It's still an introductory workshop, and we'll talk about how extrusion technology can be used for texturization of vegetarian proteins and making whatever you call smart proteins, mock meats, meat analogs, right? Various names that we are using in the industry today. So welcome all of you, and hope you have a great day today. It's long. I'm guessing it gets tiring in front of the computer. We have a 1 hour break in between, but hopefully you will survive the 5 or so hours of the workshop, four and a half, 5 hours of workshop, and hopefully we'll survive that. Yeah. So today's speakers, Abdul and myself will lead the first 3 hours of the technical sessions. And then we have Siddharth from Good Food Institute, who then we are partnering with the Good Food Institute for today's workshop and partnering with Brabender for today's workshop. So Good Food Institute and us have been talking to each other for quite some time now. And when we discussed this idea of creating a series of workshops on proteins, both of us had a mutual excitement in some sense around this area. So we said, why not partner and get together and do this? So this is the first of those workshops. And Brabender has been a partner for us. They have supported us in creating our laboratory. And they also, we also got trained in their laboratories in Germany, where Abdul and myself went and spent a few days. And they've also been very helpful in partnering in these workshops, and hopefully this relationship will continue. We hope to have other partners as well. I mean, these workshops, it's a multi-stakeholder. If you really want realization, it's a there are multiple skills which are required. Certainly skills in an understanding of protein sources is required. Sattva Phonics is there probably on the call or joining, and they have expertise in extracting proteins, and they understand proteins to a different level. There are analysis companies which could come in as well. So hopefully this workshop will grow as more and more dimensions get added. We also are assisted by Manoj and Shubham, who are research fellows in our pilot plant, and extremely excited about this whole area of proteins. It's not part of their work program, but they willingly give time to this and clearly enjoy it a lot, right? And a lot of the material that you will see today, the videos you'll see have been created by help of Manoj and Shubham as well. Yeah. So that's a brief intro to all of us. The speakers will introduce more when their turn comes. Yeah. Overall, the content of today's workshop, we begin with, I mean, first hour or so, we'll talk about proteins in general. From whatever experience we've had over the last year of interacting with a lot of different people on proteins, many have come to our pilot plants to conduct trials. We felt it is important to actually talk a little bit about proteins and what we are trying to do. What is protein? What are we trying to do? Why are we trying to do that? So 1 hour or so about proteins. Then about coming to the actual texturization of proteins, principles and techniques. And so we spent a couple of hours there talking about the theory of fibration, the various techniques, largely focusing on extrusion. No, we're not going to talk about shear cell as such. That's a very nascent technology, but extrusion is the most popular technology. Then we'll introduce twin screw extruders, the protein sources, the operating parameters, which are key, right, to the whole thing as to what are the various parameters that we can control, and why do we need to do the experiments. And then we'll talk a little bit about the protein products. How do you go from protein to making a product, right, that a consumer uses? And just some thoughts on protein sources and market products. And this is the overall content. GFI will present a part of this content, and Maria will present from Brabender will present part of this content. Siddharth has a very interesting, from Good Food Institute, has a very interesting presentation giving you an overview. And they've been instrumental putting together this whole community in globally as well as in India around the whole area of texturized proteins or meat analogs. Yeah. So, okay, so coming to this, the proteins, nutrition, and challenges, no, and why texturized, trying to answer these questions in the first few slides, as I said, and so we'll start here. So, I mean, a generic slide saying what we eat affects us as well as the world. We've all hopefully become aware of this. I mean, that food is important to our health was always known. I mean, we knew about it for a long time, but we never really thought of that it affects the world. What we eat affects the world as well, right? And if you look at health holistically, we humans cannot be healthy unless our planet is also healthy, right? So there is a connect between our well-being and the well-being of the universe, right? And this is the starting point of proteins, I would say. Yeah. So well-being for us, human health, human nutrition, slide on what proteins mean to us as such. Well, protein is one of the macronutrients, as we call. No, we have carbohydrates as a macronutrient, we have fats as a macronutrient, and we have protein as a macronutrient, right? So if you look at this cartoon on the right side, you will see that the human body, about 60% or so is water, right? 15% is fat, right? 5% are various other things which are in there. About 15 to 20% of the human body, right, is made of proteins. Yeah. Amino acids, it says, amino acids are the building blocks for protein. So about 15 to 20% of the body is made of proteins or their building blocks, amino acids. So that's a very, very significant part, actually second to water almost, you could say. Fat and proteins almost equal. So they are a very significant part of the human body. So that's the structural component, you could say, right? And the enzymatic. So what are these proteins doing in our body, right? They are part of the structure. Muscles, for example, they are proteins. Enzymes are what are called as the workers, right? You can imagine our body comprises of many workers that are taking materials from one place and putting them in another place. And that work of carrying molecules from one place to another is done by enzymes, which are very, very specific, yeah, to do very specific, specialized tasks, right? So that's the enzymes that are made of proteins. And lastly, of course, is the source of energy, right? Which is what we are most familiar with. 1 gram of protein gives us about 4 calories of energy, right? And 4 calories of energy, total energy that we require is about 2000 kilocalories of energy is what we require. And 1 gram gives us 4 kilocalories of energy, right? So protein is a major source along with carbohydrates and fats. That's why these three are called macronutrients, because these are the 3 main sources of energy for us. Yeah? So that's the 3 roles, right? Source of energy. Of course, source of energy, it gets broken down into energy and that's gone. But then the structural component in the enzymes is what constitutes this 15 to 20% that I have in the cartoon on the right side. And because proteins are getting used up all the time, broken down, denatured all the time, we need to keep replenishing them. And the guidance given by nutritionists is about 0.8 grams per kg of body weight, right? So if I weigh about 60 kgs, 60 kilograms, then I need about 60 into 0.8 grams, which is about 48, 50 grams of proteins I should have at least in my diet, right? At least. Yeah. Most of us are looking at 12% of our, 15% of our calories coming from protein, which means that maybe it's higher than 0.8 that we are looking at, but this is at least a minimal requirement that we're looking for. Okay, there should be a balance amongst the various nutrients, right? On the left side, we have the balanced diet. It doesn't mean that all of them are equal quantity, just indicating a balance between the various macronutrients, the proteins, the fats, the carbohydrates, and the micronutrients, the vitamins and the minerals. We have a third category now, phytonutrients also, which I'll not talk about today. But many a times, And for a lot of people in the world, our diet is not balanced enough. And you can see the protein part especially seems to be smaller. The carbohydrate part is
Excuse me,
actually
sir.
way bigger than. Yes.
The audio.
Uh, okay. You can hear me, right? Can I be heard? Abdul, are you there?
Now you can.
Yes, sir.
Yes, sir,
We are
yes.
able to hear you.
Okay. Yeah. Thanks, Sridevi. So yeah. So let's look at our dietary needs, right? And what protein does to it. So this is another calculation here. We've said, let's take our calories, 2000 kilocalories per day, right? And what is important is that all calories are not equal. Some calories are coming from carbohydrates, some from fat, some from protein. So what does nutrition science tell us? Nutrition science tells us that about 50 to 60% of our calories, let's say 55%, needs to come from carbohydrates, about 30% from fats, and about 12 to 20%, so let's say about 15% from proteins. So which means if 2000 kilocalories, and I'm looking at the table now, 55% carbohydrates, 30 fats, and 15 proteins. Therefore, 1100 calories need to come from carbohydrates, 600 from fats, and 300 from proteins. That's just multiplying 15% of 2000 is 300. How many grams of protein do I require? Well, I said that 1 gram of protein gives me 4 kilocalories, which means about 75 grams of protein is required to give me 300 kilocalories of proteins every day. So I need to be consuming, according to this calculation, about 75 grams, right? And then 7 grams of fats and 275 grams of carbohydrates every day to get this balance between the three macronutrients. So 75 grams of proteins is what we require. And where can we get it from, right? This is a picture which shows where we can get it from. Hopefully you can see it's small, but hopefully. But to the left of this picture, the one with the big peaks in there, okay, the y-axis shows what percent, right, of or how many grams of proteins are there in 100 grams of this product. So the leftmost, for example, is chicken breast piece, right? And which shows the number is about 31. So it means that if I have 100 grams of chicken breast that I buy in the market, fresh waste and cook it, I'll get about 31 grams of protein there. Remember, for a 60 kg adult required 2000 kilocalories, we said about 75 grams a day. So one chicken breast ka piece khaya, about 30 aa gaya. And you can see that most of the things on the left side with numbers which are high enough in 100 grams are non-vegetarian foods, right? And then we have beach mein aa jate hain, so we get the vegetarian foods like the soybeans and beans, the legumes aa jate hain. And then towards the rightmost side are the vegetables like cauliflower, etc. And all the other vegetables will come in. About 5% se kam hote hain unke. So of course, protein rich sources are going to be non-vegetarian, right? In terms of grams per gram, right? And then the legumes, right? Or the beans and the pulses and the lentils and the dal, the rajma, the chole, right? Which have a reasonable amount of protein as well. So these are the various sources of proteins, right? So now question, of course, is why vegetarian protein? So now that we know that we require proteins and how much of proteins we require, the question is why vegetarian proteins are we talking about? Why are we talking about texturization? So there are three main points why vegetarian proteins have caught an interest, right? And you need to look at globally. In India, yes, our diet is rich in vegetarian proteins already, right? We have a lot of dals in our diet. We may be meat eating as a country because largely I think 60-70% of the country is meat eating, but our meat eating is not that I have 100 grams of chicken breast every day, right? I have 100 grams of chicken breast even if I'm meat eating. I have it once a week and I call myself a non-vegetarian. I'm not having a chicken breast at every meal, right? So my main protein source is either dairy, right, or lentils, dal, right? No matter who I am in this country. But globally, yes, outside India, non-vegetarians could be the non-vegetarian foods, meats could be the major source. So question is why vegetarian proteins from a world view, right? Well, the world population has grown 30% from 1990 to 2010, right? Over 20 years, a massive increase in world population. we're nearing 8 billion, as we say, right? And heading towards 10 billion by 2040, 2050, right? Uh, so the consumption of proteins from animal products, right? So while the population has grown by 30%, our increase in animal proteins has been disproportionately higher, right? That's one key point to understand, right? So we have been shifting globally, and even in India, you could say that the more and more non-vegetarian proteins are coming into our diet, right? Uh, to satisfy this expanding demand, right, for livestock, for poultry, for animal proteins, there are serious issues of environment and sustainability, serious issues of ethics, and some health consequences as well. I mean, one example, that production of animal feed, you can see, has to increase by more than 60% to cater to this growing animal protein habit, population of about 30% or so. So that's a disproportionate increase in devotion of land to animal feed products. Right? Where does protein come from? And just maybe a little bit of chemistry here. We will have some more chemistry in future slides. But one of the key components of proteins is this thing N. Upar maine structure likha hua. On the right side, on the top, you will see a structure of a protein, a cartoon, a schematic of a protein, where you see C and H and OH and O and N. That blue dot with N in there is nitrogen. Nitrogen is about 15% of the molecular weight of protein. And where does this nitrogen come from to get into a protein? Right? Plants are making proteins, and some bacteria are actually fixing the entire nitrogen. So our air is full of 70+%, 78%, 79% is nitrogen gas in the air, but we cannot use that. Right? Hardly any animal form can use that nitrogen from the air. This nitrogen is a gas, and it needs to be fixed. You can think of it needs to be fixed so that it becomes, from a gas, it becomes some kind of a solid that can be consumed by life, right, on the planet. And this job is done by very few bacteria in the world, and those bacteria seem to like to live in the roots of lentils, our pulses and our beans and our rajmas, etc. Right? So, and that was the only way that nitrogen is brought into a life cycle, a human life cycle, or living cycle. And the graphs on the left side, there are shows that how much of our population, right, how much of our protein is being provided by, or nitrogen which is being used as protein is being provided by natural phenomena such as nitrogen fixation by these bacteria that live in the roots of some plants. And the question is, how are we producing this extra nitrogen? Because see, till about 1930 or so, the nitrogen which was getting fixed by bacteria was sufficient to support the human population. Around till that was still our population about 3 billion or so. Beyond that, right, we've now gone way beyond the limit, as we say, of natural nitrogen to support human life. Or to support any life, no? Not just human life. We now require a process called Haber's process. It's a chemical process which sucks in nitrogen from the air and converts it into fertilizer, as we call it, like urea. And that's process called synthetic nitrogen fixation. Haber was a German scientist, a notorious scientist, because he didn't do it to make fertilizer. He did it to invent bombs, which uses the same during the World War II. But it became a process after World War II to create fertilizer, and really took off. And you can see that as the human population, that's the blue line, has been going up, the red line, which indicates the synthetic, the gray line niche is the synthetic line. And you can see that really takes off from about 1950 onwards, starts increasing. And that's what is supporting a lot of our population today. जो हम बोलते हैं कि fertilizer चाहिए farmers को, right? They are basically taking this nitrogen fertilizer, which has been fixed in big industrial complexes, and that is supporting almost half the life. The picture on the right side may be more instructive, where the gray area, the shaded gray area, is life on the planet, which is supported by natural fixation, and the red part is that is supported by industrial fixation of by Haber's process. So whenever industrial process of fixation comes in, yes, we can do that, but it is very energy intensive, right? So that's the whole point, that nitrogen is important. Nitrogen is a key part of our proteins. Proteins are important. They require nitrogen. To make them available to plants, we use fertilizers, which come from almost half of this nitrogen comes from a synthetic process, which is extremely energy intensive. So if you look out now at an energy value, for example, of how much of energy goes into making 1 kg of protein, well, if you are looking at soybean, then it is about 30 megajoules of energy. But it is on the right side, you have beef, 1300. So can you imagine the number of folds of energy which is required? Right? Energy efficiency of these things, therefore, if you look at, you can see that things like milk, etc., are high, and the vegetarian sources are even higher, right? But things like beef and meats are like 1.9% energy efficiency. So 98% of energy being used is not getting into proteins. So that talks about the energy part, that how energy intensive these the animal proteins can be. And this is again a similar point, but from a carbon footprint point of view, where you can see that again the non-vegetarian sources, beef is there, lamb is there, shrimp is there, even cheese, right, and pork and chicken and eggs, they are way higher than. At the bottom is nuts and peas and beans and tofu. So the vegetarian sources have lower footprints compared to the non-vegetarian, is the whole concept. So if we want a sustainable planet, right, and we want to reduce the carbon footprint of what we do, then what we eat becomes extremely important as well, right, from a sustainable. But we do need proteins. So how else do we get proteins? We get from plants. Therefore, we are saying that, hey, we need to make a gradual shift, because as we go over the next 20 years, 30 years, from a population of about 8 billion to about 10 billion, if we continue feeding the additional 2 billion with the same level of proteins from animals, then if we meet our requirement from animals, then it becomes almost a unsustainable planet. Right? So the environmental impact of this production escalation is indisputable now. Right? Everybody has come to agree to that. Right? The emissions of greenhouse, the water pollution, the deforestation, the resulting increased meat production from animal proteins has a very high impact on carbon footprint. Right? Various numbers that you will encounter, and I'm not particularly saying these are correct numbers, but they are indicative numbers. So producing 1 kg of beef produces about the same amount of carbon dioxide as driving 100 kilometers in a car. Right? So that's the kind of pollution. It takes 15 kgs of vegetable feed to produce 1 kg of animal protein. Right? So, so these are inefficient processes, as we call them in chemical industry. Right? So, so how do we? That's why the interest now grows, as the interest in sustainability grows, as the Paris Accord gets signed by the US as well. Interest in sustainable sources of food, and in particular proteins, is growing. There is this other issue which is there, which is the animal proteins and ethics question, right? The way we farm our animals today, poultry and animals for meat today, there humans are beginning to understand that, hey, the way we need to do this to get proteins at the cost that we want is certainly doesn't seem very humane, right? And so there is a big animal ethics question around, which is growing, right, and influencing decisions of policymakers, right? Also, there is some concern around human health itself. I'm not talking about the nutritional deficiency part, but the health part, that are there any negatives of animals, eating animals? And there are links which are emerging, not necessarily just because of say toxic substances or carcinogens being there in animal proteins per se, but because of the way we are taking care of our animals or growing animals, in confined spaces with a lot of antibiotics, and then a lot of preservatives and nitrites, etc., that we use to make and process the animal meats. There are concerns, which is why the IARC, which is a WHO based body, research body that focus on carcinogens, right? They have come up with this listing of group 1, group 2A, group 2B, group 3, group 4 of ratings of various foods that they go through. They've certainly not rated all the foods. It's a very small section of foods that they have looked at. But some of the processed meats, the meats are part of 2A, and some of the processed meats as group 1 even, right? Because of nitrites in sausages and mince meats, etc. So, so there are these emerging health concerns which we have to be careful about, right? And together, these three dynamics of are shifting. The sustainability question, the ethics question, and the health question are causing a shift towards, are making people rethink alternate to animal proteins. And when you look at alternate to animal proteins, there are multiple sources, right? Plants is one, and our focus for today is, of course, plant, but there are fungi which are there. There are microbial cell cultures. There are animal cell cultivation. So there are lab-grown meats, for example, that are getting looked at. There are insect proteins that are getting looked at. So there are a number of other sources that people are looking at. So what is the target audience? What is this whole opportunity, therefore, for meat analogs? One certainly is this whole flexitarianism that you may have heard, which is ki, hey, people who are eating meat on a regular basis, can they cut down one occasion, 2 occasions, half the occasions in a week, and move to an alternate source, a non-animal source, non-dairy source of protein? Is one which is driving this movement. And many people are joining in. If you look at the numbers in Europe, especially countries like Netherlands, etc., there seems to be a massive movement, right? Sitting in India, we may not feel that, but if you are in Europe, in the US, you will see this as a big trend, right? It is no longer a fad; it has become a trend, right? But here in India, I mean, when I look at this whole thing, I look at it from a deficiency perspective, that hey, proteins, we are deficient. If we could make eating proteins more, give a wider variety of products, right? Tastier products with proteins, because today if I have to eat protein, dairy is there certainly, but dal mein dal banate hain. I mean, all the vegetarians, so largely in the form of dals and maybe pakoras or bhujia, etc. Maybe some sources that we have, but can we create more variety, right, in there? And so that's why flexitarianism and more, I'm writing, where more is where people like me come in. We're trying to look at tastier forms of eating. So, so those are some markets when you think of. I can see from that many people are from companies and startups, etc., in interest. So trying to understand the consumer space is extremely important, and seeing what you're trying to target, right? Which set of consumers are you trying to target? Key challenges, of course, of making people adopt proteins, three, I think. The first is a scientific challenge, which is nutritional quality. As we'll see later, we'll talk about what nutritional quality is, but not all proteins are same. When I present the chart, when you see the chart, say meat seems to have 30% protein, soybean 35% of the protein, mung dal 25% protein, rice about 5% protein, right, etc. That we see. It doesn't mean that they are all equal in quality. So what does quality of protein mean? It's the amino acid profile, and we'll talk about that in the next few slides. Then there is taste and texture, right? We don't eat things just, we are driven by taste and texture, right? So it's always taste plus health, not health plus taste. Taste always comes first. So that's a challenge for all the community, the scientific community, the technology community, the food community to tackle. And then lastly is that of cost, which many times, most of the times, cost is what dictates our choices, right, for the masses. So that's so these are three challenges to solve. So are all proteins alike? That's the question. Well, proteins are made of building blocks. Just like a house is made of bricks as a building block, proteins are long chains, different colors chain dikh raha hai aapko niche in different shapes. And they're made of 20 different types of bricks called amino acids, right? And together, these 20 kind of bricks can be arranged in many different ways to create about 100,000 different kinds of proteins in the human body. I mean, let's say 100, there's other people think it's about 250,000 proteins, but let's say 100,000 different types of proteins in the human body. So that's a lot of, so those are the building blocks, right? 20 building blocks. Incidentally, Hargobind Khurana, I don't know how many of you know his name, but he was instrumental in trying to figure out how these proteins get assembled, right? From the mRNA to proteins. And that's what he got him the Nobel Prize long, long ago, right? So amino acids are the building blocks, and the upar bilkul is the structure of the amino acid. Amino acid, the two words amino and acid. Amino is something with a nitrogen, NH2 group, that's on the left side. Acid is something with a COOH, right? It's carbon, oxygen, oxygen, hydrogen. That's the carboxyl group that's on the right side, right? So that's what defines an amino acid, that these are these two groups, and it's very basic. One slide on chemistry that I will have, or two slides on chemistry, and then we'll move on. But I think it's important to understand what an amino acid is. It has a amino group, which is nitrogen. It has a carboxyl group, which is an acid. And then there is a R group, a side chain as it is called, right? All of these are attached to a central C atom, a carbon atom. So there's a carbon atom attached to an amino group, attached to an acid group, attached to one hydrogen. And on the other side, the fourth bond, it can have four friends, right? And the fourth friend is a R or a side chain. Now, what happens on the side chain? What choice does it select as a friend for this four? The other three are fixed, right? It's like family. वो fixed है, वो change नहीं कर सकते. But the fourth one is a friend, the R group, the side chain. It can change. It can select what it wants. And depending on what it selects, there are 20 choices it has. And that makes the amino acid 20 different types of amino acids. And these side groups have different properties. They may be some which may like water, and that protein becomes dissolvable in water. Others which may like some oils and fats, they become oil soluble. So that they define how the protein will interact with other things in a food, and also amongst each other, and also how a protein will start folding together. Will it bring the family together into, and what shape will it bring the protein together, right? As a long protein together. Will it be as a long string, or as a beta sheet, or as a alpha helix? There are various shapes that those side chains help connect it, right? So that's the defining feature. And this gives you, we don't need to remember this, but this gives us on the right side about 20 different amino acids which are important for human life, right? Our proteins in our body are made of these 20 building blocks, as I said, right? And you will see that some of these blocks are arranged in different groups, right? 5 big groups, A, B, C, D, 4 big groups, right? And that's based on their charges and neutrality, what I was speaking about, whether they are water loving or water hating in some sense, right? And depending on the friend, the side chain that they have. But there are some blue and red dots I have put in there, right? Which are important from a consumer perspective and from a nutritional perspective. Together, the blue and red dots, see, most of many proteins, out of the 20 proteins, there are many which our body can make on its own. Right? But there are some which the body cannot make, right? So if the body cannot make, it needs to take in that amino acid, right, as is from its diet. So there are 9 amino acids which our body cannot make. And the remaining 11, the body can make, or can make partially, at least, right? The ones the body cannot make are called essential amino acids. The quality of a protein is defined by how much amount of essential amino acids it is. Because I may have a huge amount of protein in my diet, but if it does not contain any of the essential amino acids, then the remaining amino acid is useless to me, right? So what if I'm having 30 grams of 75 grams of protein? I can have 75 grams of protein, but if the essential ones are not there, that 75 grams also cannot be used by the body. The body needs all of them together to make a family of protein, to make a protein. Otherwise, the amino acids are useless to us. So that's an important point to remember, that we require essential amino acids. And so the quality of a protein is the how much amount of essential amino acids is there. The red ones I have also put in there are some of the branched amino acids. And I put that because today, if you go to any gym, right? So an urban gym, and you will look at protein shakes has become such a big deal. Uska label padhoge to BCCs likha rahega, right? Which are branch chain amino acids, right? And branch chain amino acids are associated with rebuilding of the muscles after the exercise, right? So that's something that a lot of the youth of today are after. The science is telling us that branched are important for rebuilding, while all of them are important for building muscle. For rebuilding, branch chain are important. So from an exercise perspective, or from a weightlifting perspective, from a six-pack perspective, BCCs become important. And I'm talking about all this because this should start giving ideas to the innovators, right? While everybody is today making proteins, right? कि हम texturize कर देते हैं to make meat analogs. Many of us, where will this evolve, would also start evolving into functionality. You will see over time, over the next 20 years, as we tackle the main thing of, hey, this looks like chicken, to, hey, my has more BCCs, my product has more essential amino acids, more balance. Those kind of questions will start coming in, right, that you will see. So those are opportunities for innovation, which is why I'm leaving this thought with you, right? So this was the 20 amino acids which are comprised. So let me just show. This is again just showing this concept. Maybe it's may not be that straightforward to understand, but this is a very common concept of a barrel, like a wine barrel or a water barrel. So if you look at overall proteins as the barrel ke walls, we said these 9 essential amino acids. So you can see 9 planks of these barrel, and the barrel holds water, which is our life, right, or our energy, protein energy. And if in our diet all of these are balanced, then each of the planks is high enough. That's the picture on the right side, right? That all of them are balanced and the barrel is quite deep, right? But if our diet is less in any one of the 9 amino acids, so let's say lysine is low, and you can see left side pe lysine is low, then the barrel height becomes low. It can't hold too much of water. Yeah, the water it can hold is only as much as the lowest of the amino acids in the protein, lowest of the essential amino acids in the proteins, no matter how high the others are. It's the lowest one which dictates, and that is what the quality indicates, right? So protein quality measure karne ke liye there are indices, standard methods. I will two ones. PDCAS is a very popular method, came about in the 1990s. And now scientists are saying that maybe a more appropriate one will be something called as a DAS, right? Amino acid score, right? Dietary intake amino acid score, or digestive. So there are complicated ways of measuring this. It's not very easy. You have to give foods to a rat, a mouse model, and look at how much of protein. You give a certain amount of proteins, and then you collect its poo or potty or excreta and see how much was not absorbed or how much was absorbed, and you do a balance and say this is absorbed. That is the PDCAS method. The DAS method looks at how much got absorbed in the ileum part, in the intestine part, rather than how much didn't get absorbed in the excreta. So it's a more appropriate measure, people are saying, but very limited data. PDCAS, we have huge libraries of pretty much for every ingredient. We know what's the PDCAS score, or protein digestibility score. For the DAS, the scores are not fully available, but you will see that the world will move towards DAS, which is why I put it there, that for the innovators, it is important to look at where the nutrition science is moving towards and where the regulatory regime will happen. Talking about regulatory regime, when you make a protein food, you want to label it, right? And most of you may want to label, put a claim that my food is a source of protein, or my food is high in protein, right? So when can you say something is a source of protein? When can you call a food is high in protein? Well, some indications here from a regulatory perspective that there is something called quantity of protein content in the food. 100 grams of food has 20 grams of protein in there, right? So that's the quantity. And then there is the quality part, which is the DAS score, as I said. Number one, so the nutrient reference value is how much should we have? What should we compare with, right? Well, 50 grams, as I said, is considered to be a normal value, is a harmonized value, largely agreed internationally. If 50 grams of protein is required in a day by a human, right? And so if 10% of this, your food contains in 100 grams, 10% is 5 grams of your nutritional reference value. Then if 5 grams in 100 grams of food, then you can say it's a source of protein. Or 5 grams in 100 ml of, or 2.5 grams in 100 ml of liquid, you can say it's a source of protein. Or 5% of the kilocalories, of 100 kilocalories, then also you can call it a source of proteins. Right? or 10% of one serving size mein agar aa jata hai, you can call it a source of protein. So these are various claims, right? And you'll have to look at the regulatory of your country, because I see some participants are from outside as well, and see when you can, what claims that you can choose, source of protein. And if you want to call yourself high in protein, not just a source of protein, then it should be twice the value of the source of protein, right? Yani ki 5 grams in 100 grams of food, it should become 10 grams in 100 grams of food. Then it becomes a high in protein, right? Claim that you can. And it needs to, when a food meets the criteria for protein quantity, then a quality should be applied. So only after quantity is used, then a quality measure, right? So it's an excellent source of protein, right? Which means that it has a DS score of 100 and it is high in. So it is a high source. It's high in protein and it has a high DS score. If DS score is less than 75, then you cannot make any claim, no matter how high the amount of protein in your food. So DS to aapko 75 se upar chahiye hi. Between 75 and 99, agar DS score hai, to you can call it good and a source of protein. And when you have 100, you can call it excellent and high as well, right? Cool. So hopefully you get a certain sense of this, maybe not fully understanding it yet, but wholly beginning to appreciate that these are important criteria to look at as we formulate our products, right? So we said why, we said it's not just the nutritional part, taste and texture are also important. And proteins bring that taste. I mean, many times protein bring a bad taste, right? Which is why it is difficult. Proteins are not naturally liked. All proteins are not naturally liked by people. Some like more than others. And that depends on which kind of amino acids are richer in your protein. So there are some bitter amino acids, there are some sweet amino acids, and then there are some umami kind of amino acids, right? The meaty amino acids. So depending on kaun sa zyada hai isme, so you can clearly see the meaty proteins will be rich in glutamine and aspartame, the ASP and GLU jo upar likha hai, right? And when we come to vegetarian proteins, they're largely on the bitter side, right? So how do you balance that taste becomes a very key question, right? And therefore you have to resort to flavorings and masking and other things and making sure the processing is right, right? Also, the texture part is important. On the right, I have what is the shape in which the protein occurs in my food. If it occurs as a globular form, which is like a ball, or as a fiber, which is a long chain, right? Somehow, many of us humans find fibrous shapes very interesting and unique, and they draw us to them. And so, plant proteins are largely on the right; they are globular in nature. Animal proteins also have enough globular proteins, but they also have fibrous proteins, yeah, in there. So when we are trying to create a variety from plants, what are we looking at? Hey, plant proteins, people are used to this kind of globular. Can I make a fibrous? Because that will create a novelty, a different texture, and maybe we can create unique foods. Can we get the flavor differences so that there are different kinds of flavors rather than the standard flavor that comes with the plant protein? So those are some questions that technologists started addressing about 20, 30 years ago. And over time, through incremental innovations, we have now reached a spot over the last 5 years or so, where very exciting, tasty foods are possible with vegetarian protein. So it has increased the variety of foods, yeah, which are possible to be made at a mass scale. So taste, flavor, structure, three things that have been, that scientists have been working on, which has made today's workshop possible in some way, right? To create enough interest in all of you to be here to join this workshop. So now the question is that we are trying to address in this workshop is more focused on meat analogs, right? And see, can we generate meat-like structures from vegetable proteins? So what does that require? Right, converting globular proteins to fibrous proteins is one big part of it, and which is called texturization of proteins, also called fibration of proteins, right? And as I said, upar dekhenge to these are proteins as globules. They are folded as a globule, as a ball, right? How do we open this up to create a fiber? A ball needs to be flattened to create a fiber, right? You can think of a football. First of all, you need to puncture it, and cut it open so it becomes a flat sheet as opposed to a ball. And then you need to stick many sheets together to create a fibrous structure, right? So that's what is happening that we have to do in a factory. That you have to cut open this ball, puncture the ball, cut it open, flatten it out, which is what the second, no, and we do it through, we don't have a scissor to do that or a nail to do that. We're going to puncture and denature and flatten it out using shear and heat, which is by rubbing. Shear is what? When you rub your hands, that is shearing, right? So protein beech mein dala and you are rubbing your hands, that is shearing. We do that through machines, right? And heat. And then pressure. You can press it also. Football ko press karenge to it will burst, right? Similarly, protein. So you're combining shearing and heat and pressure together to open up the protein and flatten it out, right? Once you have flattened it out, you are hoping that some of these side chains that we spoke about in an amino acid, they will start bonding to other sheets, right? And which is why the whole side chain becomes important, understanding what the side chain, what the composition is, so that we can create the right structures. And once these come together and then they start bonding, we have to create enough so that they bond together, one sheet over another, over another, over another. So you have multi-sheet structure, which is then layering of it, and that's what creates fibers. So hopefully you get a sense of it. One last point on the cost of proteins, right? Proteins are expensive, which is why there's protein malnourishment. We don't talk about carbohydrate malnourishment in the world too much, right? We can tackle it. Fat malnutrition is also not too much of a concern in the world. But protein malnutrition is. Why? Because proteins are expensive. Carbohydrates, the cheapest, one of the cheapest sources you can think of is sugar that you buy in the market, all sucrose, 40 rupees a kg, maybe, that many of us, I mean, ration mein usse bhi sasta milega, but 40 rupees a kg for 100% carbohydrate, right? Pure. Fats, right? 100 rupees a kg for an oil, maybe cheaper also you will get something, right? That 100% fat, right? So purified. So the cost of processing everything, I'm not just talking about the raw fat, right? But so this is the cost that we have. Proteins, agar chahiye aapko pure protein milta hi nahi hai 100%, but 90% or so isolates are there. About 250 to 300 rupees a kg you will get. 250 is probably the lowest that you will get. So it is so much more expensive on a per gram basis, on a weight basis, than carbohydrates and fats, right? So it's expensive. And I'm just showing this original chart. I mean, the chart that I had showed you earlier, and I'm highlighting the last two rows here. And the last column, protein, 75 grams of protein we said we require on an everyday basis. And if I put that cost of 250 rupees per kg, then it comes to 30 rupees I have to spend a day for proteins. Fat, 6.7 rupees a day to get my 67 grams of fat, and carbohydrates 11 rupees a day to get my 275 grams of carbohydrates. So you can realize now suddenly, right, that a big cost of my balanced food will be proteins. Total is almost about 47 rupees, 48 rupees, which is required to create a balanced diet for me, out of which 30 rupees, right? So about 60-70% of my healthy living cost is going towards proteins, right? And that's why when we look at, this is such a big controversial question when it comes to the nutritional, the poverty level discussions in India, etc., because we base them largely on carbohydrates and fats and not on proteins, right? So while we may have hunger met, that's the calorie hunger which is met, the nutritional hunger, we require very innovative solutions. One of those innovative solutions can come from food waste. For every kg of food we are making, we are creating many kgs of waste as well. I mean, this is just some examples: oil cakes, dairy waste, beer waste. I put tea spent, chai banaya, and whatever is left and we are throwing away, that's actually very rich in proteins. It's come from about 5% protein to about 20% protein in there, right? So if you could harness some of these waste products, so while most of us are interested in creating meat analogs, there is also huge interest. I mean, hopefully some of you will get interested eventually in, are there lower cost sources of proteins that I can go to? But you have to be very careful when you go to these waste. And this is one interesting paper that I took data from, which looked at a number of about 20-25 different wastes. This is a European paper, so it doesn't look at the Indian waste, but European society waste. And they came up with No, pumpkin kernel cake. So pumpkin ka jo waste bachta hai soup वगैरह बनाने के बाद, there's almost about 50% protein in there, right? That you're throwing away. Hard cheese waste about 40%, and so on. Hops, alcohol industry, beer industry, hops, about 25% protein that you throw away. So there are sources which are available, and you need to look at. But the quality I mentioned, you need to look at inme quality kisme acha hai, and anything above 30 is a reasonable quality. 30% of the protein, if it is made of the 9 essential amino acids, then it is a reasonably good quality protein. So there are quite a few waste proteins with reasonable quality. One other quality part that I will introduce, which is important for everyone to understand, is the racemization of protein. Racemization is that amino acid can change its shape, its contours. It's called isomerization. My left hand and my right hand, they look similar, but they are not exactly the same. I can't put one hand over another. मेरा एक thumb तरफ जाता है, दूसरा दूसरी तरफ जाता है. I have to put them like a mirror image on top of each other. Similarly, proteins, the amino acids, there are two forms, the L form and the D form, the left hand form and the right hand form, right, of the amino acid. Only the L form can be used by the human body to make muscles or for any other purpose. The D form cannot, right? And when we heat our proteins, we have to be mindful that we are not converting the L form into a D form. Right? So one check needs to be done, especially with bacterial fermentation, because more than heat, it is bacteria which can create this reversal. And this, therefore, when you look at a source of protein, you should do a check of what kind of racemization has happened. Have I destroyed my protein? Because almost it's like if you change the form from L to D, you're almost destroying protein. It's becoming worthless for human consumption. While it may appear in an assay ki protein hai, it cannot be used. So waste proteins, hopefully some interest. And if any students on the call and are interested in doing a work with masters or PhD in our lab on evaluating waste sources, then please do contact us. It's an area which is of interest to us. Yeah. So, okay, key questions, last 2-3 slides for the introduction of proteins. We are looking at the key challenges on proteins are cost, nutritional quality, and productization, which is the sensory, the taste part, right, to make it consumer relevant. For this, we require a lot of different expertises, right? Evaluation of protein sources chahiye, extraction methods of making sure proteins of right quality are coming, blending for quality of proteins. Maybe one protein may not give us the right, we may require some blends to come up with the right quality. Processing for quality, right? Microbial transglutaminase assays are there, which can actually improve the quality of proteins through multi-step process. Texturization, which we are talking about today, taste, and then prototyping skills are required. So veg proteins lab, various dimensions, protein sources and extraction should be there, texturization should be there, prototyping, what we call as the culinary part of converting one ingredient, which is texturized protein, into a food product is required, and the new product development and scale up is required, right, from there. Converting a recipe into an industrial recipe and scaling it up. And then product analysis, yeah, consumer preferences, sensory analysis, nutritional quality analysis. So this is in a schematic way that today's workshop is focusing on texturizing ingredients, creating a designer ingredient, as we call a smart protein, as we call it, right? Which then will go into a recipe and a new product development lab and get created into a food product, which will then get scaled up in a factory so it can be done and repeated in a manner to create a business out of it. So these are the challenges. Today's workshop will focus, as I said, largely on texturization part, not on the other side, other aspects. They are for future workshops. And with that, I come to the end of this introductory deck. And now open to any questions that we may have. Yeah, 5 minutes of questions, and then we can go on to the next part. Yeah, any questions? Abdul, anything on the chat? You can post on the chat, and then I can read, or Abdul can read off the chat. Any questions?
Hello.
Yeah.
Good morning, sir.
Yeah.
I'm myself Smita. I'm working on, we are from Devigiri Biosolutions Private Limited. We
Yeah.
are working on extraction of plant-based protein concentrate using novel technology, using the greener technology. And if we want to conduct these extrusion trials in Bangalore, can we have that facility? Can we come and use use your facility to make the extruded products?
Sorry, can you say again, Smita? I didn't catch the question fully. Can we use what?
Okay. Can we use our protein concentrates to make extruded products in your facility? Do we have that
Oh, yes,
opportunity?
you can. I mean, if you have sufficient quantity, we'll require maybe at least a couple of kgs to do some trials.
Okay.
But certainly they can be done. Yeah.
Okay. So what is the minimum quantity we require, sir?
At least minimum 2 kgs, I said. Yeah.
Okay. Okay. Great. Thank you, sir.
Yeah.
Good morning, sir. This is Urshita.
Yeah, Ushita.
I'm working as consultant for Licious.
Okay.
And I would like to know, once we process the plant protein or try to texturize it, what is the impact on shelf life? Does it go down considerably, or we still have good amount of it?
No, so the protein doesn't go anywhere, right? Protein, the protein, hai, it stays there. Nothing will happen for donkey's years, right? But taste, certainly you have to look at, right? Very clearly, right? So protein is not that tricky. Like, see, fats can get rancid, for example. So there is a worry that fat over storage becomes rancid. But proteins there is lesser of a concern from protein degradation based on storage, but more of a concern from a sensory point of view. You have to be careful, but then there are ways to look at that. So we can stabilize that. Cool.
Thank you, sir.
Yeah. There is a question from Harish which says, how is DIAS calculated, DIAS code? That is the amino acid score, the quality score. There are two ways of doing these things. One is that there is a database, people are putting things together and you just read off what is the DIAS score for a certain protein. The other, if you are doing it yourself in a lab and you want to start making claims, you have to do a DIAS test, and there are third-party laboratories who will do that. Largely, it is done by using a rat model, right, a mouse model, where a protein, the food is actually fed to the mouse, and then it's for the DIAS, its blood sample is withdrawn to see how much of protein has been absorbed by the intestine, by the ileum part, and for PDCAS, it is the excreta, right, or the poo of the mouse, which is taken and analyzed for, and then a mass balance is done versus what was fed to what was excreted, right? So, but there are experts who will do this job, right? The purpose here was just to introduce that these are important concepts to know about, right? I wanted to know, Ashish is asking, I wanted to know what are the key factors driving plant-based meats. I mean, as we said, there are three main factors which seem to be driving it. One is sustainability. Second is animal ethics. Third is the health concerns related with meats. And that's what is driving in the West. In India, that of course is a very niche market. So I think what will also drive going forward will be creating tasty products, and people will buy because it is tastier than something else that they have consumed. So that should be the focus for everybody right here. If you are interested in making to how do you taste should be the focus. Could you please explain the difference between fibrous protein and globular, how denaturation can be controlled? Well, fibrous and globular, as I said, in terms of main difference from a sensory perspective is in terms of its texture, right? The globular proteins have don't have a fibrous texture, right? So their chewiness, etc., hardness, chewiness, they are very different from fibrous proteins. So if you want to create a variety just doesn't come from having different ingredients. It comes from different, for proteins, texture plays a huge part in the mouth. And so creating a range of textures is important if you want to put variety on the table. And so fibrous proteins have fibrous textures. And how do you create this fibers? Through denaturation of protein and then putting them together as fibers. No? And that can be controlled, yes, definitely, by moisture, by heat, by shear, by pressure. These are 4 things that we use in a factory to control the fibration process, the denaturing the fibration process. Cool. Yeah, sharing slides. Abdul has already mentioned we'll share the slides. Cool. Okay, should we go ahead to the next one? Any other questions, burning questions? Happy to answer them. Okay, cool. I mean, really great to see. We've touched 50 participants. When we launched the workshop and we floated out, I had thought about maybe 10 to 15, but 50 clearly shows there's a lot of interest in this area. So thank you for everyone for joining this call, this workshop. We'll move on to the second part. Abdul, can you come on? Are you there? Abdul will be moving to the laboratory. He's shuttling between the pilot plant and the laboratory. And I will start my second deck here, which is now moving into the texturization part, which is what most of you have come here for. And okay. So yeah, we'll begin here and then we'll be doing a dual act because Abdul will, we have a lot of videos and some live, taking you through the laboratory that Abdul is coordinating with Manoj and Shubham. Abdul, whenever you're on the call, or Manoj and Shubham, do unmute yourself and pitch in. Okay, so introduction to texturizing vegetarian proteins, right, by the extrusion technology. Hopefully now you have an understanding of what a protein is. Protein is made of amino acids. Not all amino acids are same. They are different based on, some of them can be used by humans, the others cannot. Some of them can be synthesized by us, some cannot. So essential amino acids, our food should be rich in essential amino acids. There are implications of taste. There are implications because of the side chains being different. The binding is different, and therefore implications on the creation of the fibrous structure, depending on what amino acid source we are using. And we'll give some intro to all of this. Remember, this is an introductory workshop. The purpose of the introductory workshop is to introduce some of the concepts. It may not be possible to explain them fully, right? But hopefully it will excite and create an interest for you to come back, either read in textbooks more and try and understand that, or reach out to us to try and understand more about these. Right? So, well, there are a few processes now. Some of them have reached industrial scale as well, or at least a pilot scale. Extrusion is, of course, the single biggest process which has reached industrial scale for making texturization in proteins. And then you will also hear about a shear cell technology which is emerging. One company has it, Rival Foods. It is not as popular yet, right? But maybe there is some more action going forward on shear cell technology, etc. But our focus today is largely on extruded foods for this. And so let's spend a few minutes talking about what is extrusion, right? Extrusion, simply said, is a process that converts raw materials into a product with the desired shape and form by forcing material through a small opening. I joined a company, Hindustan Unilever, in 1998, and came across the first extruded, that was my first exposure to extrusion. And you know what we were extruding? Soap. So soap is an extruded product, right? It is forced out just like this and then cut into bars and stamped. Upar Lux lik diya, Lifebuoy lik diya, Hammam lik diya, or whatever brand that you're using. It's an extruded product. So extrusion, you've probably seen in so many different products, not just food products. Extrusion is a very common way of making products, right? All the plastics that you see, right? A lot of the plastics that you see are extruded products, right? So extrusion is a very common unit operation, as it's called in industry. food extrusion is a relative novelty, right? So, and last 20 years, certainly it has picked up a lot, right? It's been going on for about 50 years if you read the papers, but 20 years it's picked up a lot. In last 5 years, the texturization vegetarian proteins has picked up a lot. So hopefully you understand when you go to the market now, जब आप soap देखेंगे, you will understand how it's coming out as an extruded product like this and then getting cut into the shape, right? And similar with plastics that you see, extruded plastics. Now food extrusion bola to food is actually also a polymer, right? There are two main polymeric substances in food. One is called starch, the other is called proteins, right? And in between there are fats, and together these three comprise most of the food along with water. Water I call as a plasticizing agent. Plasticizing agent is anything which will make things flow, right? Is plasticizer in foods. And then we have small molecules like vitamins and minerals and other things which play a very important role from a taste perspective, from a structure perspective, and also from nutrition perspective. But two big sets of molecules, starch and protein, right? And when we are doing food extrusion, either we are looking at the starch mein kya karna hai, which is called gelatinization and breakdown of starch. That's the and then protein mein it's about denaturing the protein and forming fibers, right? Those are the two broad areas of changing the molecular structure of food, right, to get it to behave and create products that we like. Cool. Today, of course, we are focusing on protein part, right? For processing of protein. Processing of starch is for another day. That's pastas and Cheetos and kurkure, right? That's for another day. Noodles. So when we talk about extruder has two main parts. There is a screw section, right? It's like two big screws, which is red mein dikhaya hua aapne. You can see two screws. That's a twin screw extruder. Twin meaning do hai. So that's the screw section. And then you have a die section. Die section is basically a small hole. And that's the shape that you want to push your material through. Right? It's almost like if for those of you who've made homemade bhujia, right? You don't have an extruder, but you have a pocket जिसमें कि मतलब pressure से कर रहे हैं, but there's a nozzle at the end. That's the die, right? जिसमें and you can create different shapes coming out, right? You can continue because it's a continuous process, unlike the घर का भुजिया वाला process, which is a batch process. You have to have a continuous supply of your dry powder, plant protein powder. That's the first supplier, and then you need to keep adding water. Right? And the remaining part, you'll see both these are added early in the portion, and the remaining part of the screw is mixing them together, kneading them together. Right? Dough बना रहे हैं, गूंद रहे हैं जैसे आटे को. So it's together. It's putting pressure on it. It's shearing it to create whatever denaturation is required, if you want, on the molecules, and then pushing it out from the die. So screw section system within a barrel. It conveys, it mixes, which is it's blending, it's kneading, it's shearing, and then the die section is extruding through a small hole. Then the extrusion process, right? We talk about extrusion process as two words we use: multivariate process and a complex process. हमें लगेगा ये तो कितना सिंपल सा चीज है, घर पे भी तो ऐसे ही एक्सट्रूड कर रहे हैं when we are making bhujia, right? But we call it a multivariate and complex. And what do we mean by that? If you want a controlled process, multivariate means there are a number of variables in each of these two sections, right? It's not just one variable. We spoke about pressure as a variable. We spoke about temperature as a variable. We speak about RPM, how fast the screws are moving as a variable. So those are all variables, right? Process variables as they are called. And there are many of them, right? Similarly, in the die section, there are a number of variables, pressure hai, temperature hai, right? And then there are the shape variables, ki what kind of a screw it is, right? What kind of a die it is. So, and each of, so that's the multivariate. Multi means many and variate is variable. So when number of variables are controlling the final output characteristics, it's called multivariate. Complex is when each of these variables are kind of linked to each other. They're not independent. अगर आप एक change करेंगे, so then everything else also changes. Right? That's called a complex because the variables are interlinked. They're not independent variables. And not only are the variables connected, but the variables of one section are linked to the variables of the other section. variables of the screw section affect the variables of the die section, and variables of the die section impact the variables of the screw section. So the sections are directly linked to each other, which is making it ultra complex. So those are two thoughts I wanted to leave you with, and which is why, and we don't understand the effect of all these variables fully. Yeah? No scientist in the world, yeah, today completely understands, which is why we have to do a number of experiments with any mix, right? And we can't just sit down and put down an equation, and if you want this, ye chicken chahiye, to ye ho gaya, and done, right? You have to keep experimenting to create, right? So and how do you play? You play with heating and cooling, you play with mechanical energy. So you are putting an energy in this operation. This energy is either directly through heat, you are heating the barrel of the die with steam or electricity. Then there's mechanical energy that you're putting in with the motor, and there you have moisture, you have shear, you have pressure. So these things that you are creating in there, and you're playing with these as variables to see what happens. So some of the variables, as I said, screw section. Well, you could think of screw configuration itself, as a variable, because you can, in a twin screw extruder, you can change the screws. Yeah, they are almost like Lego blocks. They are put together like small elements or small blocks to construct a long screw, and you can change the configuration. So that becomes a variable, controllable variable. Unlike in a single screw extruder where you buy once and that's it, right? You can't change. Screw speed is another one we spoke about. Barrel temperature profile. You can change that profile through the barrel, not just ek set kiya, right? But through the barrel you can change. Similarly, die section, the die geometry, the cooling rate, the flow rate. So those things are variables. Complex, we said any change in one section impacts process conditions in the other. For example, cooling rate in the die section affects the pressure and the filling degree in the screw, because backward impact, it's going to create a pressure which moves back, because thanda ho gaya in the die section. There's a pressure built up all the way back. As pressure also builds up, material builds up, and therefore there's also filling degree which have changes happen. So number of variables, you change one parameter somewhere and all the way back an impact is felt. It's like a traffic signal. Aage one car gets stuck in front and you have a kilometer long jam, right? It impacts somebody who's like 1 kilometer behind. So that's the complexity of the process, right? We've never been able to solve a traffic problem. It gets worse and worse, but hopefully the traffic jams in a screw conveyor we'll be able to address through our understanding of the pressure and the shear stress, etc. And that's what we are doing when we're doing our experiments. I spoke about the screw configuration and the dies. So on the right, you see pictures of various kinds of dies, right? There are some long and some short, but you can see also different kinds of holes through which it is coming out. Rectangular, ribbon shape, or circular hole like a noodle, right? We have shapes like rice granules which can be made, like dal granules which can be made. So the number of things, because you have cutting technology along with the extruder that you can do further. The longer dies are the dies where cooling can also be done in them, right? So the longest die only partially on the right side below you can see with cooling block as well there. That's the one for protein, for HMM, the high moisture melt proteins, right? On the left side, you see various designs of screws. These are small elements about 1 inch long, which are then put together on a rod. And I have a picture. And these elements can do various jobs: mixing, kneading, shearing, right? And then other heating operations. So this whole twin screw extruder, while seems like one unit operation, is actually a number of unit operations. If you're trying to do this in a regular factory without a twin screw extruder, you would require these 7-8 unit operations, and you'll require different tanks for these, right? All of them are now possible within one single equipment, right? So it's a very simple, compact equipment, which is why it's gaining so much in popularity. So today, food production and processing extrusion has established itself as a technology that is routinely used to create very high quality food products, tasty food products, attractive in price, because it's very compact, very simple, right, to do. And its starting material, as I said, are starch or protein based products. Yeah, one of those two largely that we are focusing on. But many things which cannot be handled by normal processes, such as dark flours, wheat bran, broken rice, etc., can be handled through extrusion processes. So it is very flexible also. Not only is it compact, It's very flexible. And the processing range within one extruder, if you look at a batch vessel, there's only so much of flexibility you have, right? But here within an extruder, I mean, the extruder we have in the pilot plant, we can run at 2 kgs and we can run at 20 kgs also. Can you imagine a tenfold? We have a batch reactor that we design and build for making chawanprash and and ghee. We can change from, I can work at 3 liters, I can work at 5 liters, right? Scale. The window of operation. There are 2 kgs, so you can imagine hardly a 1-fold change in my batch operation, but almost a 20-fold change here. Right? That's the power, right? For anybody familiar with industrial processing, that's the power that this gives. As the processing range within an extruder is very wide, the die and screw geometry is also exchangeable. So I can create many different. So within one unit operation that we have, we can do pastas, we can do noodles, we are making snacks for iron deficiency anemia, we are making snacks for diabetes, type 2 diabetes. We are incorporating botanicals in matrices, in starch matrices, in protein matrices, right? So there are so many other things besides fibration that can be done. Candies are made through it, pet foods are made through it, right? A huge amount of things can be made through extruders. And subsequent treatment of what comes out in the extrudate, like drying and roasting and coating, creates a novel range of products. So they are becoming, extruded products are becoming very popular. And I think it's a breakthrough moment in industry. It will only grow, right, as the costs come down further. And you can already see examples, directly expanded products like corn curls, Cheetos, right? Expanded products like pasta, half products like potato pellets, which can then process further. Co-extruded products like fruit-based cereals, jelly-filled cores, right? You can do filling, modified starches, texturizing of meat analogs, which we are focusing today, candy like licorice. No, you've seen licorice strings, which are quite popular in European markets, like chewing gum, etc. And protein-based products, we're talking about texturized vegetarian proteins, semi-moist expanded pet foods, sausage products, surimi, caseinades, processed cheese. So a number of examples of that people have tried with, right, with these things. So mainly, like, coming to now the actual food extrusion process, there are 3 steps that we are looking at, right? In your mind, what are we doing? We are doing some kind of a thermal treatment and a mechanical. Thermal means heat. We are putting in heat and we are putting in some mechanical energy, heat energy, mechanical energy, 2 types of energy into a process. What does that energy do? That is causing some changes in the molecular and microstructure, right? It changes molecules, changes the microstructure. Microstructure is something you will have to look under the microscope, right? Small. And that results in physicochemical changes which impacts the macrostructure and the product properties, right? So those are the 3 things that we focus, right? And the better we understand these 3 things, the more consistent our process becomes, and the more we can do with this technology. The whole thing started, as I said, more than 50 years ago. And the earlier products were low moisture extrusion products, and pastas, and there was some of the first in the large scale extruders, which were where we started, right? And you can think of also high temperature, short time process evolved. It's cooking which happens in a minute, right? Where else can you cook within a minute? But this allowed you to do that, extruder. So high temperature, short time. Largely used with low moisture content. I keep thinking, and maybe they're already there, but even big when we talk about midday meal programs, when we talk about langars, right, where we have to feed masses. What if we start looking at extruders as the cooking platform itself? I know it's already being used in many places. There's a lot more which can be done for mass cooking, and I think more and more foods will move towards this format. The second generation of this happened 1980s onwards, so that's also now 40 years ago, but largely maybe you could say 1990s onwards, so 30 years ago, is the high moisture extrusion cooking, right? Where you're plasticizing food mixes at high moisture content, ranging from usually about above 50, but above 60 to about 80% or so. And a lot of this work happened in Japan and some in France, Montpellier, and the National Food Research Laboratory in Japan, where the early work in protein fibration started happening around that time. And that's what we are talking about largely. We're building on the leads that they generated in our workshop today, right? And so the advantages of extrusion, versatility. Hopefully, when somebody asks you what are the advantages, versatility is one. You can do so many different things with it, and adaptability. You can adapt that same thing to do different things, right? The same equipment that you once buy. Cost of the final product, while the upstream cost, the upfront cost may be a little higher, but over time it's way lower. Productivity, it's higher throughput, smaller footprint, product quality is more comparable, and it's environmental friendly, right? You will look at the total waste that you generate, even things like water requirement for cleaning, etc. I mean, it will be way lower than similar things in other processes. Types of extruders, there are two main types of processes. You have ways that you can classify. Single screw and twin screw is based on how you construct, whether you have two screws or you have a single screw. For protein texturization, twin screw is the one that we use, right? And then method of operation, cold extrusion, hot extrusion, high moisture extrusion. Depending on how much of moisture, the first two, cold and hot extrusion, are low moisture processes, and high extrude moisture is the HMMA, the protein texturization process with high moisture, right? So these are broadly the types of extrusion operations, right? Single screw, say when we go to twin screw co-rotating, which is the one we use largely, you're increasing the mechanical energy that you can put into the process. You're increasing the consistency of a process. You're increasing the flexibility, the variety of things that you can do, the operating conditions that you can play with. And you're increasing the cost, the capital, upfront capital cost, not necessarily the overall cost, but the upfront capital. Just a quick word around what does co-rotating and counter-rotating mean. Co-rotating, pehla screw, both the screws are rotating in the same direction. Whereas counter-rotating, they are rotating in the different direction, right? And that co-rotating is the one which has become extremely popular. It has high pressure regions and low pressure regions, and better for mixing and moving things forward, which is why it has gained in popularity versus the counter-rotating. Yeah. So the variety of products that are created through a twin screw extruder are huge. You could pretty much create anything that you wanted to. And certainly for meat analogs in texturizing proteins, twin screw extruder is the one which is required, right? You have way more flexibility there than anything else. Cold extrusion, temperatures largely below 100 degrees centigrade, pasta, noodles. Hot extrusion, temperature above 100 degrees centigrade. These are ready to eat snacks, and if you want puffing, you definitely want 100 degrees centigrade and above, and largely to do with starchy materials more than protein materials. Hot extrusion also with the making the low moisture proteins as well. That's where the first protein started. Right? And then we'll move to the high moisture extrusion process for texturizing vegetarian proteins, which is above 100 degrees centigrade. This is relatively higher moisture, right? So how is the extruder setup? So now let us just quickly look at how is an extruder setup. Extruder is set up, this is a schematic of a extruder. We have the extruder barrel. We have the die at the end with a knife assembly to cut whatever is coming out. And then we have the live bin and the feeder at the top. So we feed the powder at the top in the live bin. Then there is a conveyor belt or a screw, which will be the feeding screw. Then there's some kind of a preconditioner, and eventually comes to the extruder barrel, the main barrel, right? And you require motors, you require gearboxes, etc., which are all below, hidden usually below, right? So that's a basic assembly. As I said, the die and the barrel and the feeding bin are the three main components that you have to be mindful of. When you look at the feeder, the feeding bin, well, the feeding bin has to ensure, one of the most important to get a good product, to have a uniform regulated operation is how are you feeding? Your feeding has to be consistent. Whoops, end of slideshow. Sorry, it has, I will go back and check. Sorry, it just threw me out. I'm going back. to my proteins workshop. Yep. Just bear with me a minute. Hopefully you can see the screen again.
Yes, we can see.
Yes, sir.
Okay. Okay. Yeah. So as I said, most important is consistent feeding. If you do not have consistent feeding in your experiments, then you're pretty much doomed, right? You cannot get a consistent product, right? There are two types of feeding: volumetric feeding and gravimetric feeding. Volumetric is, are you feeding the same amount of volume, right? Gravimetric, are you feeding the same amount of weight? Gravimetric is of course better, but is also way more expensive and also requires a lot more maintenance, right? Volumetric is cheaper, right? What we have in our, but volumetric is also good, right? ऐसा नहीं है कि volumetric is bad. Most processes will have volumetric and it is fine. But point is, you require at least one of these two operations, right? Once your feeding is set, right, then you have to look at what kind of screws in there. And there are a number of different types of screws, we said. So screws are defined by, I mean, decreasing pitch, for example, that you can see right on the top. What is pitch? Pitch is the gap between the two threads in the screw, right? And you can see that the gap keeps reducing as we move forward. So that's a decreasing pitch screw. There's an increasing pitch screw. There is a threaded barrel, which is the barrel itself also has threads in it. The barrel is the outer part and the screw runs within the barrel. The conical barrel is, the barrel is cone shaped, the screw is evenly shaped, right? And so the gap keeps changing. Alternate pin and pin type screws are there. There are pins. Pins are the barrel is protruding in, right? And there's something, I come from the tea industry where rotor vanes are there, which is something where a barrel is moving. There are a lot of pins in there for disrupting the leaves. So these kind of different types of screws are available, as we said, screw and barrel assemblies. This is how a screw looks. The pitch, as I said, is the gap between two threads. There is the barrel within which the screw moves. That's the barrel diameter. Then there is the screw root, which is the base of the screw, right? Then there are the flights. The angle of the flight is important. So there are, and then the clearance between the screw and the barrel is there, which is called the screw.
Hi, Sant.
I'm calling from Mumbai. I'm an automotive writer.
Right. Hi.
Earlier this week on
I think somebody needs to mute. Someone's voice coming up. Yeah, hopefully everybody's muted now. Cool. So there are different screws, and these are, you can see here on this picture, there are two rods at the back, right? This is the rod which goes and gets fixed in my twin screw extruder. We have a 800 mm, which is 0.8 meter long rod in our pilot plant extruder, but they can be a few meters long, right, in a factory scale one. And then you have screw elements. Each of these screw elements is a few centimeters in length. And you can see they are hollow, each of these screw, because they get slided onto the, you load them onto this rod, right? And you stack them together. Jaise chudi pehna rahe hain. So it's almost like you're putting chudis onto this, this rod, and they fit very well. Their ends are so clean that when you put them all together and you tighten, lock them at the end by the lock nut, they appear as a single screw. Right? This is just a cross section of the different types of screws which are there. Right? You can see some of them are what are called as conveying elements, right? Which are just normal screws, but their pitches are different, right? Some are, the two top ones are ones where the pitch is smaller, and the next three where the pitch is bigger. The gap between the threads is bigger. Then you can see reverse pitches there, right? Niche in the second line, the third and the fourth, the direction of the thread is changed. It is reverse pitch. The screw is still, the rotor is moving in the same direction, but because the thread is reversed, it is now pushing material back. So there is forward mixing or there is reverse mixing, right? Which is happening. So that can happen. Then you have things like kneading blocks. So in the third row, towards the right, the four elements, they are called kneading blocks. They are for goond rahe hain, jaise aata goonte hain na, the dough that. So they are called kneading blocks. They have more shear that they are putting in. Then there are disruptor blocks, yeah, which are there in the bottommost row. In the middle, there is one disruptor block, which will cause some disruptions, yeah, to the dough that is needed. more shear in there, or breaking it apart, basically cutting it and disrupting it. So these are various unit operations that happen within the screwing element. And as you put the screws together, for various purposes, we put different elements in different configurations. So when we say a screw configuration, how am I deciding what configuration, what screw, what element goes first? Is it the forward conveying one which goes first, then followed by a reverse element, then followed by a kneading one, then by a disruption block, then by another kneader, then another reverser, then another conveying forward? I can keep changing. You can think of there are infinite options by which you can align them together. And that's where the expertise comes in, that how do you put these together, right? Is one key part of the expertise, right? Here is actually a simpler picture showing the forward conveying element, the screw. And then you can see forward conveying element, but with the shorter pitch, the gaps are lower. That increases the compression. Then the third one below that is the reverse element, because the direction is changed and now it will reverse and push material back. That keeps the material in there in the screw for a longer period of time. Because आपका length तो उतना ही है, I can't change my length. 800 mm, 0.8 meters is my length. But I can change by adding a reverse element. I can increase the time the material spends within that. Then the kneading blocks are there, which I said are for the dough, and then the rupture blocks, which will cut, right? They increase mixing, the food, they cut. So these are the different blocks, the shapes of the blocks. And this is a picture of our screw. Here we've opened up the barrel. You will see there is half the barrel upar dekhenge bilkul on top of the slide, the two shapes there, the U-shaped, they come down and lock the screw completely, right? So it is a barrel which is completely circular, but it is cut open, and so we can open it completely and see inside. And then you see the screw. The screw is moving from on the left side, on the right side where it's all white is where I'm feeding it in. And then you can see the conveying elements, they are moving things forward. They have a wider pitch initially, then a narrower pitch, and you can see the compression beginning to happen. The temperature is also building up, so that's also causing the color change, and then starts becoming brown somewhere, right? And those are where the kneading blocks and the disruption blocks, we have kneading blocks which are coming in, and then reverse blocks are there, and then it gives move. You can see the color change happening, right? Along as the heat starts building up. On the where it is white on the rightmost extreme, the temperature is only around 40 degrees centigrade. Whereas on the left, the temperature we had increased to about 120, 130 degrees centigrade, right? So, and so you can see how the progression happens, right? So that's the advantage of a lab scale unit, that not only do you get your product, but you can open up and see what happened within the screw after the run is done, and where are things going right and where are things going wrong. And that gives you a very good idea as to what elements you have to change, right? What configuration, if there are any configurational changes that you need to make, that you can get a good sense. So that becomes an important part in there. Extruder dies, I've already covered this, that very many different kinds of dies can be attached to the end of the extruder section, extrusion section. And for proteins, we have the longer dies. For the HMMA, the high moisture ones, we have the longer dies where we require cooling. For the low moisture extrusion, we have the shorter die, and sometimes we require a heating there actually rather than a cooling, right? So that's a difference. Again, another picture, maybe more clearer here. The longer die at the left, you should be able to, when you see these dies, should now become very clear to you which one I need to use for a high moisture extrusion, right? The one on the right, which is the longest die, and you can see the small little pipes, the nozzles, which you can see the 6 nozzles there. Those are the ones where you put in cooling water, right? Then you see the circular die in the center at the top. That also has nozzles on the side. There you can put heating water. That's for the dried product, for the dried texturization, low moisture texturization. So number of dies, and then the shape of where the die head finally from where the material is actually coming out. You can have all sorts of shapes, circular shapes, very thin noodle-like shapes. There is one at the bottom on the right where it's almost like an annular shape. And then you have a rice-shaped die in there as well. So various shapes which are possible. So that's what gives flexibility here, because you can mix and match. Right? To get an extruder, you require a number of other things, not just the extruding screws and the screw elements and the die heads, but you also require volume feeder that we spoke about. You also require a cutting device that we spoke that is required at the end when things are coming out. How frequent do I cut? So there are knives with a motor which go round and cut. Then there are feeder and cutting device controller units are there. How the feeding controller is there, my cutting device controller is there, the RPMs they will operate at. I require water circulators. Multiple water circulators are required to do the job fully. Then you require vacuum systems. You require peristaltic pump to control the amount of water which is going in. We require cutting blades. We require to measure things. So pressure transducer, thermocouples, etc. are required. Burst pin, which is the safety pin, is required. If pressure builds up too much, and the burst pin comes, just like a pressure cooker safety valve is required in there. Because finally, it's a pressurized unit, actually way more pressure than in a pressure cooker. So it is a dangerous unit unless you have proper safety measures. And it's been now studied so well over the last 20 years that huge number of safety measures are in there, and the safety valves are one key part to it. And then, of course, all sorts of very specific tools are required, especially the torque wrenches, which we show on the left, because if you don't tighten these things enough, there can be leaks, but also we can destroy our whole kit together. The screws, the threads for tightening can get destroyed if you're not tightening them properly. So it requires, to run this unit requires 3 levels of almost. You need to be a very good technician, right? You need to be a very good engineer, and you need to be a very good scientist, right? 3 things together, because heat and mass transfer is what engineers understand. Putting all this together is what a technician understands, right? These tools. And the scientist is understanding as to what is happening at the micro level and at the macro level, like microstructure, molecular structure. So those 3 things. So it's a tough ask, and some tools for cleaning, of course, which are required at the end. So these are all pilot scale tools that we are showing from our unit. And at this point of time, I will stop and I will stop sharing my screen. Any questions you have, please fire, and Abdul will take us through a live demo session, right? Before we come into the principles and the technical part of it. Abdul? Any questions while we wait for Abdul to join?
Sir, kindly shed some light on the cost and capacity of the machinery or the setup.
See, I can talk maybe GFI Siddharth later on, and maybe Marie can speak a little from Brabender, can speak a little bit more about the cost of big scale unit. From the unit that we have, the pilot plant unit is quite costly. It is costly because it is specially designed for a flexibility, comes with a lot of different enhancements, etc. So I would say the overall investment of having an installed unit would also nearly come to anywhere between 1.5 to 2 crores rupees, right? To have a functioning unit which can do a lot of different things, right? Not just protein texturization, because we have a number of die heads, we have a number of different screw elements, and number of side kits, so conveyor belts, etc., accessories that we have designed for making a very functional unit that can do a number of experiments. So it is quite expensive, and in that sense, but this is a pilot scale unit. The actual investment from a factory point of view, as I said, when you start comparing the overall cost, not just the capital cost of an equipment, because twin screw extruders you can buy now for 20 lakh as well, right? A large unit you can buy for 20-30 lakh, but they will have lesser flexibility, etc. We want something which is engineered so that I can open it, I can close it, I can see what's happening. That costs a lot of money, right? Which is why a lab pilot scale equipment costs way more. Industrial scale units may not cost that more. I mean, similar my scale, which is 20 kg per hour, they said 15-20 lakhs I can get from China if I want to, a good unit. working unit
Right.
will do the job. It will not have the ease that we want for research
Yes, sir.
purposes, but will do the job. Yeah.
Thank you for the answer, sir. Sir, I also wanted to know that like what will be the R&D cycle like for per product if we are going for an R&D or research, and what will be the development process? How much days or months will it take to create a perfect product like
See,
from a basic
that question
perspective?
that question has no easy answer. That's a question which keeps coming up again and again. It has no easy answer. Getting a first product out, a first prototype out is a matter of 2-3 days, right? That will give you a reasonably satisfactory product. But winning products in the market require a huge amount of iteration. I mean, something as simple as tea that I worked on for 20 years, to get one process going would take us like 10 scientists working for 2-3 years to create something, and you don't even notice that as Naya Taj Mahal or a new Brook Bond or a new, right?
As a consumer,
yeah, as a consumer, right? But the amount of effort that goes behind to tackle all the issues, is massive. So it all depends on the person who is doing it when they are satisfied, right? If you are satisfied in 3 days and you can find a market, it is fine. But and you can take years in developing a product if you have something specific in mind. But I think to me, you have to take it in stages. You start off with a 3-day thing and say, where do you reach in 3 days? Then you will also learn, right? By tasting, by giving it to a few people, and then deciding what next to do and move forward with it. Right?
Yes. My question was more related to the standardization of the process. Like, how do we standardize the process? Is there, a regulatory authority which is governing over these process?
No, the regulatory authority is for the final, so not necessarily for the process per se. I'm not a regulatory expert, so I should be cautious. So don't take my word as the final word. You have to go to the regulatory experts for that. But I mean, regulatory, you have to basically register your whole factory with FSSAI and ensure food safety and stability of it, which you can get challenged on if something goes wrong, and you to therefore produce data at that time. But otherwise, it's very straightforward to do a FSSAI registration, right? You have a site, you register the site, you have a product, you register the product, you have the nutritional profile, you go by the labeling requirements which are there on the FSSAI site, and that's it.
Right. Thank you for the answer, sir. That's it for me.
So it is very easy. I mean, for proteins, it is not a novel. It's easier, right, in some sense. Yeah.
Right. Thank you, sir.
Yeah. Cool. Abdul, are you ready?
Hi, sir. I'm Vijay here.
Hi, Vijay.
Yeah. So actually, in the last session, I've asked this about this fibrous and globular proteins. Like, how does it affect when we, do the extrusion product, and also how we can control this denaturization. So when you talk about this twin screw extruder, there is we classify into like counter rotating and also rotating part.
Yeah.
So how does it exactly affect this process parameters that we optimize for low moisture product? Is there any criteria like where I can optimize from the raw material itself, the type of starch or protein content, fat content, what I add to the product, and how can I go for the process parameters, variables that I can set for this low moisture product? Is there any basic funda around
yes,
it?
I mean, pilot scale trials are for that purpose, that you can do a number of experiments with very little material. As I said, 2 kgs per 2-3 kgs, you can run for an hour and try out a couple of conditions. So what you are saying is exactly what a pilot unit does, that it allows you to do a number of different test conditions for shear, for RPM, for temperature, etc. Screw configurations that you can change, right? And each of them the second part of my talk will address some of those things. So hopefully we'll understand that a little more. Right. And
okay.
at the end of that, if you have any more questions to ask, yeah, cool. Abdul, you come on wherever you are ready.
Mute.
Yeah, Abdul.
Sir, am I audible?
Yes, you are, Abdul. We'll take the questions a little later. So I know Sushmita is asking for a question, maybe to unmute, but Sushmita, if you can just hold on. Yeah. Abdul, go ahead.
Sir, hello everyone. Today I will take you to the virtual pilot plant tool. So this is our these two extruders. So I will just open this is the cover. This is the 800 mm barrel, which can be split up. There you can see the two grooves in that where a screw can be fitted in, and it has 20 mm diameter and 800 mm length, and we have 4 openings at the top and 2 side openings with 4 heating zones. We can add additional heating zones also in the dissection, additional 4 heating zones, and there is a monitor where you can control all the parameters like screw configuration, screw speed, feeding rate, moisture content, and temperature, and many other things. So we need additionally, apart from this extruder, we need some circulators like water circulators. So it helps in monitoring the temperature within the barrel to heat it up or cool it down. And this is another water circulator, cold water circulator, which can be used for texturization, the dye which is used for the texturization. So that dye should be cooled. So to use, so we use this one for cooling the dye. So I will show you the dye. So this is a cooling dye, which is 300 mm length with cooling ports where the water circulates in the jacketed form. And we can add a temperature if you want to measure the temperature or pressure at any point of the die. Let's say if you want to measure the temperature of the product which is exiting from the die, so you can connect a thermocouple. These are the thermocouples, and this is the pressure transducer. Right? So it measures the temperature and pressure. And there is this dye, cooling dye is used for high moisture extrusion, where the moisture content will be around 65 to 75%. And for low moisture extrusion, TVP extrusion, we use generally a round die head with an heating element in it. So we don't use a cooling die here, since the temperature will be more higher than what we use in the high moisture extrusion. Here for low moisture extrusion, the temperature will be around 160 to 200 degrees centigrade. While in case of high moisture extrusion, will be going up to like 130, 140 degrees centigrade, and then sudden cooling to let's say 35, 40 degrees centigrade. And for low moisture extrusion, there will be a cutter which is attached to this. And there are different kind of blades, as Dr. Gumi sir is mentioning, like 2 blades, 4 knife blades, and 8 knife blades, based on what product format you want. Um, you can use it along with that. If you want longer product length, like longer dimension, use it like 2 knife dies. If you want small granules kind of a product, you can use it like 8 knife blade. And these are the a brief description about the dice. And let's just move to the another part, which is a very important part, screw configuration. As Dr. Gumi sir is mentioning, a screw plays a very important role in texturization. Uh, so you can see different kinds of screws here. So these are the conveying blocks which conveys forward the material. And there are kneading blocks here which kneads the dough and creates a shear within the barrel. And there are some reverse elements. Here you can see, right? It's in the opposite direction, which holds the material for a longer time within this screw. That intensely creates the pressure within the barrel. And after that, it moves forward to the end of the screws, and then it enters into the cooling section. And yep. This is it. We'll be taking some short break. And meanwhile, if you have any questions, you can ask. And after that, we'll be going to the demo session where we will set up the extruder. And after that, we'll run a trial. And you can see both the processes, high moisture extrusion and low moisture extrusion, how it is made and what are the different parameters that can be controlled during the process. And yeah.
Cool.
So if you have any questions to ask right now, or
hello, sir.
Yeah, go ahead, James.
Okay, so regarding the high moisture extrusion, so how do you reach that moisture around 65 to 75%? Do you add it uh, during extrusion in the extruder or in the dry mix?
No, we add it in the
so
extruder,
we have
James.
different ports on the top of the barrel. See, let's see, this is the first port where you can enter the feeding material, which is usually a dry powder. Let's say for protein texturization, we use protein isolate or protein concentrate. We'll put them. We have another accessory, which is a feeder. This is a feeder where you put the material in it, and it pushes the material into the barrel in the first zone. And we have another peristatic pump. It's a small peristatic pump. We can use this pump to input the water into the second port. And the water and the material mixes within the barrel, and you can calculate so you can calculate the moisture content at what moisture content you want to extrude the product. See, if you want to extrude the product at 70% moisture content, you calculate the moisture content of the feed material, then how much water you need to input, just calculate, and then you can add the water into the barrel. That's how you can calculate the end product of the extrudate.
Okay. Okay. Is it important to where you add the water? Does it have to be at the start of the extrusion, or can it be in the middle or on the third zones?
Usually we use it for this second zone for
Okay.
putting the material, putting the water in.
The water.
And we have a third and fourth zone where we can use for some of the ingredients which are heat sensitive. Let's say if we are using a flavors or colors which are heat sensitive, then we can add those ingredients in the fourth or third zone, right? Just to minimize the residence time within the barrel.
Okay. Thank you.
So Abdul, you make your way to the lab for the next session.
Okay.
And thanks a lot, Abdul. Thanks, Shubham. Thanks, Manoj. I know you were behind the scenes and helping.
Thank you, sir.
So yeah, this was to just introduce and give you a picture of a live session of how our lab looks like. And we will take a short break as Abdul walks back to his desk in another building where he will then beam the videos. So it's a 5-minute break. For those of you who want to stay online, I'm still here, so I can answer some questions in the meantime while we wait. But it's 11:56 according to my watch, so 12 o'clock, 12:01 is when we'll start. Cool. Any questions? Please feel free.
Sir, good morning.
Yeah.
Sir, I'm having a question regarding HMMA extrusion. At what stage should we add fats to the extruder?
I mean, fats, again, you have to experiment with. So whatever we do, we are adding, if we are adding any fats, right now we don't have, if I talk about, adding fats, I think you need to look at it separately. One, do you need to add during the extrusion step? If you are adding, if you are making a high moisture melt product, you may not need to add any external fat to it. For a TVP, you may want to add a little bit of fat upfront itself, along with the others in the second stage, maybe third stage. You have to play around and get when we do our processing, we add it at actually we are not adding in our trials yet because we have only 2 ports which are active at any point of time. Otherwise, you can add it at the third port, right? The third, which is around midway, you could say. And a lot of the materials themselves will come with some fat, right? So chickpea flour, for example, will have some fat in it itself, which means it gets added right front. But typically you want to have less than about 2% of fat, etc. in your extrusion process, 2-3%, less than 5% certainly in the extrusion process. The other place where you add fat is after you have the extruded product and you are now into the culinary part, right? This is just texturizing the protein. Once you have a texturized protein, then you are mixing it with other fats, such as if you want a solid fat, which is what most people want, then coconut oil is the oil of choice. But that's in the culinary part of it, right? Where you start adding fat. Hopefully that gives you a sense that if it is something, many times fat comes along with the soy ingredient. Chickpea is one I give you an example, in which case it'll be there right from the start. You preferably want to, if possible, want to add fat somewhere midway, not throughout. So a third port would be a good place to add fat. Otherwise, there is a flexibility of incorporating fat post the extrusion when you are actually making your final product. And HMMA, that's the place where you add some fat. Yeah.
Sir, good afternoon. This is Vasant here.
Yes, Vasant.
Sir, my question is, have you tried about this amaranth seed protein isolate or concentrate on the HHMA?
When you say seed protein, meaning?
Amaranth seed protein.
Oh, amaranth seed protein. No, we haven't tried amaranth. We haven't played with amaranth yet. I mean, if you want to, if you have amaranth seed, you want to play around with it, more than welcome, right?
Okay, thank you, sir.
Sir, there's another question.
Yeah, James.
For TVP, is it are TVPs only high moisture products, or can it also be low moisture?
Yeah. So I mean, when I look at texturized proteins, I don't know what the official lingo is. I know some people think of TVP as only HMMA products, but I think texturized vegetarian proteins to me is the whole range. The dry products and the wet products. The things which have moisture below, which are so if you are extruding things at below 50% moisture, they are largely the dry products. And to stabilize them, you have to then take them through a oven almost immediately and get them down to below 10%, 5, 6, 7% moisture. That's the dried process. The HMA process is usually above 60%. Below 60, you don't get good texturization. So you're above 60%. And then the moisture, you keep it at that level. And so you are then going through further processing, or you are going through a freezing and storing. So you require a cold supply chain or a frozen supply chain, or maybe a retort, at least a retort.
Okay, but for the low moisture TVPs, can we still achieve that same texture, same meaty texture?
You can get meaty textures. I don't know if you can see it, but I have a packet of dried products which Abdul and team made in the lab. And they are very nice. I mean, they are stable. They have 6-7% moisture. You need to hydrate them before cooking. And so because they're quite hard, like granules.
Okay.
And
so you just need to hydrate it. Okay.
Yeah. But your question on can we get as good a texturization, the flexibility of HMMA, the high moisture is way more than this. Much more things that you can control there compared to this. Not saying that good products are not possible here. I mean, it is. But the reason why high moisture is creating interest is because of the greater range of products.
Okay. Okay. Thank you.
Yep.
Hello, sir. My name is Harish.
Yeah.
Sir, I have a question regarding the water activity. So, for a high protein food, is the water activity as important when compared to a food source with high carbohydrates, something like that? From a storage perspective.
I think we are still. I will not answer that question because very limited expertise, experience. Expertise is very little experience on playing around with water activity of these materials and how that will impact stability, etc. We follow. I mean, we have a water activity meter in our lab, and but I will hold back on answering this question in a very concrete way. Right? We haven't played around with that parameter yet.
Thank you, sir. And just a follow-up question on what would be the cost of setting up extruder in a pilot facility?
As I said, extruders are available for a wide range of costs. As low as 20 lakh rupees that you can get an extruder, a pilot scale facility done. So, I mean, you take about 20 lakh for the extruder, you will require, if you're making an HMMA kind of a process, you then require your other utilities like a chiller plant, cooling water, chilled water, etc. Yes. You'll require heating, so steam se hai ya electrical hai, so boiler chahiye. So you come up with, I mean, you'll have to do your own costing and see what all, is it a brownfield, is it a greenfield, are utilities there? But yeah, as low as if everything else is available, you already have a facility, a lab, and you want very simple, not the kind of pilot plant that we have. What we have created is a facility that can create serve anybody's needs, right? It's a very flexible pilot plant. The model that Brabender has is designed for that kind of a purpose, for R&D labs. But if you're just looking for pilot plant, once you've done your R&D, you've narrowed down your parameters, then you go and order a something which is less flexible, more for your particular process. And that is cheaper. Right.
Understood. Thank you, sir.
Yeah.
Sir, hello.
Yes, Smita.
Sir, what would be the shelf life stability of the high moisture meat products plant-based?
Yeah, I mean, the shelf stability of products which are out there is quite high, up to a year, like any other food product, as long as you are complying with the instructions on the pack, no frozen or yeah. So it is possible to create long shelf life products, right? As long as you follow the supply chain.
Okay.
So yeah.
Thank you, sir.
That's my answer. Yeah. Abdul, whenever you are back, please come on so that we stay on time.
Okay, sir. Sir, I am in the lab, so we can start the demo session now.
Okay. Yeah, let's start. We'll hold the rest of the questions for later, but yeah.
Okay.
Go ahead.
So I'm sharing my screen now. Okay. So we'll go for a session which is how to set up an extrusion process for a high moisture extrusion. So first we need to set up the extruder. So we'll start with configuring the screws. This is how the shaft look likes, and it will be fitted to the vise. And we have different kinds of screw elements. So this is how we just insert the screws and then we'll tighten it with a screw tip with 10 Newton meter just to ensure it is fitted properly. And after that, we need to check whether these screws are properly fitted and it is positioned correctly. So we just roll onto the a plane surface these two screws, and then if it rolls properly, then we can move further. And after that, this is the cover. Just open the cover, and this is the barrel as I have shown earlier. You just open it up and insert the screws. And these screws will go into the gearing box. So these are the two side plugs which can be attached here. So if you want, some material to be inserted at these positions, somewhere near to the middle, so we have another kind of feeders where you can push the material forcefully sidewise also. So always we use a lubricant. This is the food grade lubricant which is used in the screws for the tightening, just to prevent the corrosion and to bear the high temperatures. And after that, we attach this ring nut adapter. After that, this adapter again then will be attached to the die. It's a universal adapter. So we have 18 screws which goes onto the top of this barrel. So we use a torque wrench to tighten this ring nut with 30 Newton meter. So these are the specifications that they have Brabender has given to follow for the safety and other things like for proper processing. And the top 18 screws will be tightened with 60 Newton meter in a zigzag fashion, like cross manner. And first we'll tighten it with 30 Newton meter crosswise, and then we increase up to 60 Newton meter. For incorporating the water, so we use the second port. So just opening the second port. So this is the pressure transducer used to measure the pressure at this point. So you can measure at any point the pressure or the temperature. So it measures up to 700 bar pressure, from 1 to 700 bars. And this is the thermocouple, which measures the melt temperature at the screw tip. So the temperature range is from like 30 degrees centigrade or 20 degrees centigrade. You can go up to like 400 degrees centigrade. And this is the burst pin for the safety purpose, and it ensures that if the pressure goes beyond 150 bars, it just bursts and release the pressure. And we need to tighten all these pressure transducer or thermocouples with 20 Newton meter. Now we need to insert a sealing ring. This ensures a proper, proper seal between the die adapter and the die. So to measure the pressure, so we use a CAN communication, control area network communication, so which is in the serial form. It connects to the extruder and then to the pressure transducer and then to the feeder, so which completes a circuit. So these are the ports where the stock thermocouple goes in. So this is the 300 mm modular cooling die, which is attached to the adapter, ring nut adapter. So we use a sickle spanner to make sure it is properly tightened. Just for the support, we use supporting, triangular shape supporting. And for water supply, we use these 6 openings, and it is connected to the cooling water circulator, which I have already shown you in the pilot plant. So I have used another thermocouple to measure the end product, which is coming out just after the die. And another pressure transducer. Usually at this position, the pressure is quite less than that of at the ring nut adapter position. There is a very high pressure, maybe 15 to 20 bars. Here goes the second thermocouple into the extruder. A second thermocouple CAN connection to measure the pressure. And finally, the CAN connection goes into the feeder. So this completes the setup of the extruder. And then I will hand it over to Dr. Gurmeet sir to discuss on the texturization process further, and then after a few slides we'll see a trial using a soya concentrate as a feed material.
Thanks. Thanks, Abdul.
Oh, thank you, sir. Yeah.
So hopefully you got a good sense of of how an extruder looks like. Oops, sorry. Share. Yep, share. So can you all see the slides now? Yep.
Yes, we can see.
Yes, sir.
Yeah. So now we come to the process part. The principles of, there were some questions earlier about how do you control the process. So hopefully you will start understanding now that you understand the need for proteins and texturization. You also have some idea about how an extruder looks like and some basic setup, etc. Let's now look at the process itself, right? And what do the parameters do? If you look at the schematic below, right? These are some important steps in this whole transformation of plant proteins to meat analogs, right? So we have a plant protein source, soy protein isolate, chickpea flour, wheat gluten. Somebody said amaranth extract. So there are various sources, right? And so you begin with a seed, and then you are doing an extraction process, and so that's all the upstream work to convert that into either a concentrate or an isolate, right? Or at least, if nothing, a defatted flour, right? A flour, when you powder it, it becomes a flour. When you take a seed and powder, it becomes a flour. And then, depending on what you're doing, removing things and making it more and more concentrated, going from defatted flours to concentrates to isolates, right? You need to get to a protein concentration about 60% and higher to start the texturization process. So once you have that, by combining your various protein ingredients, you get into a texturization process. And what you get out is a texturized fibrated protein. This protein is then converted into some kind of a product. That's a primary product that you send to customers. Most consumers will actually want a finished product, which means you have to do something more to it, right? So that's overall what we are trying to look at. And our focus for today's, when we say about processing, is this texturization process, right? So extrusion, it's a combination of chemical processes happening and some physical processes happening, right? Thermomechanical cooking is a very common name that you will see, because when we cook at home, we are just doing thermal cooking usually, right? The mechanical part is something we can hardly do at home, right? We don't introduce too much of shear at home. So mechanical part is what gives us a flexibility, and that's why industrial cooking is thermomechanical cooking. And the interesting thing about a extruder is, can you change the amount of, if total energy input is 100, how much of it is from thermal and how much from mechanical? Can you go to 10% thermal and 90% mechanical, and the entire range to 90% thermal and 10% mechanical? That's what you're trying to do, right, in a flexible process. And of course, then the fibration part, which happens in the die, that not only thermomechanical, but it's not just heating, but there's a cooling part also, which is extremely important. In a kitchen, you would do the cooling part if you have a refrigerator, right? Otherwise, shelf cooling mein thoda badalte ho. So fibration starts happening. Target kya hai? Of course, target is you want to make a fibrous structure. So that's the focus today, right? There can be many other targets, but today is a schematic of what I just said. There is a globular protein, right? Vegetarian protein. If you are trying to create textures through fibration, then we are beginning with something which is a protein which is non-fibrous. So example, a globular protein. We are doing extrusion cooking, thermomechanical operation, shear and heat, and opening up or unfolding that protein into shape. And then doing allowing these unfolded sheets or together to create, and coming together is what gives the fibrous texture, and that's called the cross-linking, where we talk about that side chains. Those side chains are getting linked with each other. Of one sheet linking with another sheet is called cross-linking. Right? So that's what is happening. So it's a thermomechanical process. Shear, heat, right? Shear is mechanical, heat is thermal. Heat supplied by the heater. Also, heat is generated by friction inside the barrel. Right? Material is compacted as the screw channel depth reduces. So those are ways of, right? And then extruder screw mixes the material and converts it into a melt and orients the proteins. Yeah, that's another important word that I'm introducing, which is called orientation. Right? Denaturing opens up the sheets, opens up the globe, the balls of protein into sheets. But these sheets can be oriented in different ways, can be looking different ways. You have to make sure that all the sheets are now lined. If you're creating a stack of paper, right, you're trying to make sure that all the papers are aligned on top of each other to become a good bundle as opposed to scattered. You can take them, but they're scattered here, they're not aligned with each other. Here you're trying to align them. That's key, right? So as I said, two main energies in this process. One is called the thermal energy or STE. The other is called mechanical energy or specific mechanical, which is SME, right? Those are the two main energies. The thermal energy brought in by barrel heating or sometimes direct steam injection into it, whereas the mechanical energy is the energy because of mixing, pumping, shearing, pressure generation, mixing, right? And percent of each, right, is how much amount of energy is coming from total energy kitna and how much from steam and how much of SME coming. It becomes a useful first idea, right? So let's look at different processes. Now, our meat analog extrusion process somewhere in the middle there. And what is it telling us? It's telling us what kind of water percentages, moisture percentage during processing is there. And then how much of the energy that we have put in is split between thermal energy and mechanical energy. So it's telling you two important parameters: how much amount of water is getting input into the product and how much of energy is putting into the and what is that split of energy. So the meat analog, for example, and it's giving you a certain 40% of moisture. But of course, if you have HMMA products, they go right up to 70% moisture. And the thermal energy, you can see 30-70 here, that in this process. Whereas gelatinization, which we spoke about earlier, like starch gelatinization, if you're making a white sauce, for example, in the kitchen, you don't require mechanical energy. I can make very good white sauce on my gas stove, 100% thermal energy, right? I take some cornstarch, I take some butter, I take some water, and I mix them together. And I get very nice gelatinized starch, as we call that. So that's 100% mechanical energy. On the right extreme side is direct expansion, like Cheetos, if you have had, right? Puffed corn puffs, right? That you have. That is 90% mechanical and 10% thermal. Your whole thing is about it being heated up, but then coming out, and that pressure drop is creating the puffing. So it's a huge expansion that is happening there. So this chart is giving you the whole expanse of how mechanical different products and different mechanical energies and different thermal energies, right? From 100, 0 to almost 0, 100, right? Range. And our meat analogs are somewhere in the middle. And by playing around with that balance, that's what we are trying to do when we are creating our meat analogs. So protein texturization, two parts, the thermomechanical part, we said, and the fibration part. The first happening in the screw, the second happening in the die, right? Also in the two schematics, I have the dry process and the wet process in some sense. The dry process has raw material. In the picture, there is thermal cooking, which is on the left side. And then there's a die, which is very small. And on the right side, we have the wet process in which we have the other parts are very similar, but the die is a very long die in which the fibration happens, right? It's a high moisture process. Dry process is a low moisture process. So we require specific screw profiles for the thermomechanical cooking. These are two steps, thermomechanical and fibration. But fibration happens very differently in the two processes. Yeah, is important to note between the dry and the wet process. So both these require specific screw profiles. High L by D is a very is a requirement for most of these processes. Yeah, which means whoops. I get thrown out every time. Sorry, I need to go back to my share, resume share. Threw me out. Yep. Hopefully everybody can see it again. Yeah, so L by D, that's the length of the screw to the diameter of the screw, is usually high, right? Our pilot plant unit, for example, is 820, which means 800 mm is the length and 20 mm is the diameter. So the L by D ratio is 40 as I call it. It's quite a high L by D ratio. My L by D ratio of my batch operations that I have for cooking is 1, right? The length and the diameter are similar. So here it's 40. The high moisture, and that gives, the reason that is required is to give enough time, residence time largely, right? How much of time it's going to spend in. High moisture content usually generally 50 to 70 is required, right? The dry ones will be less than 50, but the high moisture ones will be closer to 70. Temperature range about 130 to 160, relatively long residence times are required. And then fibration, if you have the cooling dye, then fibration, you have more flexibility on the fibration, the cooling dye, which is why HMMA. The two broad, some more differences. The dry TVP process, less than 50% moisture. Wet process is usually above 60%, is our experience. Dry post extrusion and storage. So in the dry TVP process, less than 50% means 40% of process higher, so you don't have a stable product, which means you have to have a drying step immediately in that factory as soon as it comes out. Because just think of, don't think of vegetarian proteins as different from meat proteins in the sense of its safety and handling, yeah, stability. It is a very nutritious food and will catch bacteria just like a meat would, right? So somebody asked the previous section question around water activity, right? I mean, the point was about safety. Treat them as you would handle them as you would handle any meat product once the moisture, if the moisture is high, which means you have to get down to drying as soon as possible. You have to get down to freezing as soon as possible. Have good hygiene in place, minimum human contact, make sure the air is clean. All those things have to be in there, because think of it as it's meat coming out, as an animal meat coming out. Don't differentiate it in terms of its safety. So the drying, immediately that it comes out, needs to go into a dryer and oven and get the moisture down to 6-7%, right? Where it becomes stable and can be stored forever at ambient. No cooling dye is required here, right? The dyes are way shorter because there's no cooling required. Dyes are way shorter. Thoda sa heat hota and that's it. The melt temperature is about 150 degrees centigrade here. So the temperatures are way higher here. Low shear process, yeah, more heating, less shear here. We told you about that split between the two. Here, less shear is required. Fibration is not as anisotropic as what we feel, right? We need to get good SEM pictures for that. And then less flexibility in the process, right? Wet TVP, we said moisture is greater than 60%. You don't require a drying immediately post extrusion because you can pack and freeze, right? You require a cooling dye. Without a cooling dye, you will not get good fibration. But cooling dye is giving you that flexibility of creating very good fibers. The dye has to be long because it has to have sufficient time. Our cooling dye is almost, 800 mm is my screw length. My dye is almost about 300 mm, right? 200-300. So it's a very long dye. Melt temperature, because I require sufficient residence time in that cooling. The melt temperature is about 120. So when it exits the screw section and before it enters the die, temperature is about 120. It's way lower than the melt section in the dry TDP. I can achieve fibration at lower because my cooling section will help in the fibration. High shear is required here. So there's a balance between shear and thermal energy, more balanced here. Laminar fibration happens, right? So the flow is almost laminar, the sheets layering each on top of each other, and wide range of products are possible through the TVP process, right? So it's just a quick intro to do these things. Then high moisture extrusion, if we talk of, offers potential to produce, it's a wider range. And because it's wider range, people have been more successful in creating more meat-like textures, yeah, through this process. There are two parts to the process I mentioned. One I call is the physics of the process, the other the chemistry of the process. Physics is the mixing of the continuous and the dispersed phase. You know, when you look at meat, as a physicist would look at it as a phase structure, because you have water in there, you have protein in there. Some protein is soluble, some is insoluble. So there is a continuous phase and there is a dispersed phase, yeah, in a protein. So it's almost like an emulsion. And then that's what you are also looking at when we are creating this. We are looking at creating phases, two phases, and the dispersed phase is what we are trying to stretch in between. Those are the stretched parts that we see, that the fibers we see are in a continuous phase, right? The chemistry part, when you look at a chemist speaks about it, they will be talking about denaturation, about cross-linking, right, that we spoke about. So these are two different perspectives, and both of them have to come together to create a winning product. Right? And so this Zhang's paper that I put here, right, is talking about this, right? Muscle meat-like texture is achieved by imparting this anisotropic. This word anisotropic means that its properties depend on the direction. In one direction, you'll have one property, in another direction, you'll have another property, right? Just like wood, right? You have the striations of a wood, the fibers of wood एक direction में और दूसरे direction में. एक direction में काटना आसान होता है, the other direction it's difficult to cut. Just like meat, there is one the fiber direction, the other the cross direction, right? So here also you're trying to create an anisotropic, which is from something which is very similar in all directions, which is the vegetarian protein, to a directional protein, which is if you cut in one direction, you will see along the fibers, the other is transverse across the fiber cut, right? And that's by shearing and orientating the proteins. To achieve this desired anisotropic fibrous structure, the high moisture extrusion is generally operated using a co-rotating screw, right? Co-rotating twin screw will help in this, right? Along with the die, the cooling die, right? And water similar to that of meat finally, right? With the cooling slip. So about 80 maybe is too high, but 60 to 70 from our experience. During the extrusion process, plant proteins are fed to the extruder. They are mixed with water. There was a question earlier, when do we put water in there? First, you put powder in there. So that's your feeding section. Then you put water. Yes, you can put water in the first section, also becomes a little more trickier. So we always prefer to go dry powder first, then water, yeah, and then fat, yeah, and transport along the rotating screws. In the screw section of the extrusion process, the material will be exposed to thermomechanical stresses. We've spoken about thermo, the heat part, and mechanical, right? The mechanical part of it, the shear part, the pressure part, due to the shearing action of the screws and the heating of the barrel. And then the thermal part also by the cooling. Don't forget that thermal has heating part and cooling part, heating in the barrel and cooling in the die. These stresses which are induced as a result of thermomechanical treatment, they affect the properties of the plant protein. What do we mean by properties? The protein denaturation, that's the chemical reaction, the unfolding of it, the realignment of these unfolded sections. We need to make sure they are aligned, they are orientated, right? Sitting one on top of each other. The bonding of them by the cooling, that between the sheets we are creating bonding. The bonding is there in the globular protein, the native protein, the bonding is within one sheet itself, right? To create rings. What we are trying to do is we are opening it and we are making sure that the bonds are now happening between the sheets as opposed to, if it happens within the sheet, it creates a ball. Right? And then the miscibility and the rheological properties, right? How does it flow? How does it look like? This was a very famous paper, right? By Tolstoy-Guzov, who gave this whole idea about the phase behavior of the multiphasic system. So I just talked about how physicists look at it. And it's important to look at, because what does this show? This shows that there is a continuous phase and there is a dispersed phase. The continuous is a water. We are adding water in there. It's basically, you can think of पानी में protein डाला हुआ है. आपको पानी दिख नहीं रहा, because पानी is creating a structure there, but it is the water phase is continuous and उसमें protein डाला हुआ है, but there's a high amount of protein in there. Therefore, you don't see flowing water, but it's trapped water. But it's protein trapped in water, not water trapped in protein, right? And what are we doing? We are creating this dispersed phase, all some free water, but it has some proteins and disaccharides also in there. So pehla is the plasticized protein, and the other is the water and the soluble proteins in there. And this, this dispersed phase, the protein granules, we are then trying to stretch in the direction of the flow. So you can see that these droplets of proteins and water, right, are there. You're first of all mixing it and making sure that it's uniformly dispersed in this water plasticized protein. And then this is the part that gets stretched, the dispersed phase gets stretched, and that creates the filaments of fibers that you are creating. That's the physicist's view. So, so overall, I mean, the final texture of the MMA, the protein is influenced by the different types of protein bonds. And different types of protein bonds means the different types of sources, whether it's soy protein or wheat protein or pea protein, will bring different types of amino acids and therefore different types of bondings, which is why some give more fibrous, the other less fibrous. There are different factors, the protein type, the pre-treatment, the extrusion parameters, all of them influencing, right, the final characteristics. To tailor the product, right, I'm coming to point number 5, 6. To match consumer expectations, it is necessary to influence the ingredient composition as well as the extrusion process conditions on the final. So, and in the next few slides, we'll start talking about this, what are these extrusion process conditions, so that, and how can we alter the properties, the consumer relevant properties of that. Okay. Okay. So some of this in the cooling die part, the residence time is important. I mentioned it needs to spend sufficient time in the cooling die to create fibration. You can see the cartoon of the fibers, created parabolic shapes of fibers which are created. Design of the cooling channel becomes extremely important. The cross-section area and the opening dimensions become extremely important for this part, right? So die baking is also an art. This is an open die. Again, it's the die is there are 2 layers. हमने उसको open कर दिया, screws खोल दिए, so now you can see within the die. On the right side is where material came into the die, that round circular thing that you see, and then opens into a very flat rectangular die. And which is where the fibration is happening. Yeah. And once you have the fibers, you can see here the fibrous structures that are getting created with the soy isolate, 90% protein. You have chickpea concentrate, 78%. Again, some fibers you can see. Wheat gluten, you can see. Wheat gluten seems to create transverse fibers, right? In whatever experiments we have done. Very spongy material, very different characteristics. Soy creates very hard fibers, right? And so you play around with these two to create the right texture. Soy concentrate 75, the fibers are a little more softer, right? So the strength of the fibers are by operating the manipulating the operating conditions, the ingredients itself, which are you using, the screw section configuration between the various elements, the pitch of the screws, the number of forward moving screws and the backward moving screws, the kneading blocks, and also the die configuration, short and long, etc. Here is something I got from a literature which gave the sheer strength of different types. It's not a very clear picture, I'm sorry for that, but showing how chicken dry breast, for example, is softer, not as hard, but beef moist heat is way harder, 43, 45 hardness texture. It's a texture scale. So depending on what meat we are trying to do, we want to play around with the different textures. There's only one part of converting a protein into a certain type of meat. What is the texture? What is the hardness? What is the springiness? What is the elasticity, etc. There are other taste elements also that I'm not touching upon here. But this just gives you what is it's saying is that combination of measurements such as tensile or shear strengths. One is under compression, the other is under pulling, to measure things like firmness and elasticity and chewiness, allows us to describe the texture properties of the fibrated protein. Just another picture of showing how fibers in the top picture, right? Rough surface, relatively short and thick cross section of oriented fibers. Niche ke section mein the fibers have become very long, right? They are stretched further. The dispersed phase is stretched further, right? So the upper one with short fibers is more like a chicken strip. The bottom one, the stretched fibers, more like a pulled pork, right? As we say. So the strength, the length of the fibers also play a role in changing the texture. Right. So this is protein sources can play a role. Number of protein sources are used today. We mentioned about isolates, concentrates, defatted flours, and full fat flours, right? Those are 4. When you just grind a seed down, you get a full fat flour, right? Like a soy flour. If you remove the fat part of it, your protein content increases from about 30% to about 50%, and you get what is called defatted flour, right? Having too much of fat doesn't allow us to extrude well, right? So you need to get to defatted flour. 2, 3, as I said, less than 5% is okay, but not more than that. Concentrated is when you take other ingredients out and you concentrate about 60, 70% protein, and then isolates where you get to above 90%, 95%. So when you source things, the reason I put all 4 of them together is because you play around with all of these to get to whatever protein concentration you want to match with your moisture concentration, because that will affect your overall texture of your texturized vegetarian protein. So these 4 things can be mixed together, and they don't need to come from the same source. They can come from different sources. Isolate can be soy, concentrate can be gluten, defatted flour can be a chickpea flour, etc. So you can have them, various things can blend together as well. And because you're looking at functionalities, texture, mouthfeel, right? All of these coming together. The soy protein has been the most commonly used one, right? Today I write it produces the best meat analogs, but as we learn about other proteins, we will be able to make better and better products with other proteins as well. Soy protein is available. It's the lowest cost one. It is most widely available as well. And also is, because of our so much of experience, gives the best texture at the lowest possible temperature as well, I should add. Right? I can get good texture at 120 degrees centigrade. Similar things with other, I may have to go to 120, 140. With pea protein, I have to go to higher temperature to get textures. Wide variety of functionality that these proteins have, and nutritional quality is also very high with soy protein. Normal 98% that of milk and egg protein, which is the other reason why so many people have it. Right? The others you probably need to supplement with amino acids to make it a whole protein. With soy, minimal supplementation is required. Wheat protein is again good. We've had fantastic results with wheat protein as well, and a mixture of soy and wheat is gives really good results. It is however very different in texture and softness compared to soy protein. Soy proteins can get very hard, whereas wheat proteins give that element of one. It gives you texture in other direction as well, and it gives you a lot of springiness and softness to easy chewability as well. Nutritional quality, as we said, is lower compared to other plant proteins, so you need to supplement your mix with amino acids sometimes. Then pea protein, we get low texture generation, but we are beginning to get better as we start changing temperature. So I mean, at higher temperature, you start getting texture. But to us, the best quality we've got is with soy protein. But pea protein in high moisture extrusion has given good results as well, right? And because we are a chicken eating population in India, the amount of textures and the hardness that we require is not that much. So pea protein has quite a, I think, quite a future when you're looking at chicken type of or softer proteins or just tastier proteins, right? Where you're not trying to get to beef kind of a product or pork kind of a product. Nutritionally way better than wheat protein, but not quite the same as soy and egg. Egg is of course a class, one of the best protein profiles. Egg white protein I'm putting in here. It's not a vegetarian protein, but many people look at that as well to create interesting structures. And it is firm and it is brittle. So whenever you're looking a good snap, right, break like a hot dog, adding a little bit of egg protein helps there, right? And it has profile, as I said, has all the essential amino acids, but it's not vegan. So that's the big issue. There are many emerging proteins, oats, potatoes, rice, corn, moong dal. I work in Ayurveda University, and moong dal is said to be And if you look at Nitya Sevanya Ahar, which is a protein that can be had on a daily basis, Mung dal is unquestionably the one which is referred to. So I have a huge interest in my university, has a huge interest in Mung dal protein and creating structures there. So anybody who's interested and has Mung dal, please welcome to our university. We'd love to work there. Also interested in Masha dal, which is a black lentil, Ma ki dal as we call it. So in Ayurveda, that is said to be the most strengthening of proteins. So, so happy to play there as well. There are, of course, new ingredients. As I said, pulses. People are looking at root vegetables as protein sources. People are looking at seaweed and algae. People are looking at, and so this world will keep on, of special proteins will keep on expanding. We're just beginning in this journey. Wide variety of protein, importance and of process and product development. With the wide range of protein sources available, the applicability of existing as well as novel protein sources to produce meat analogs, we need to keep evaluating it on a regular basis. Whatever I'm saying today, in 6 months of time, we'll have so much more learning that we'll come back with newer results, newer ideas. And as I said, while today we can make a statement that soy protein gives the best, in 6 months of time, we may say that, hey, with protein also, we can, with pea protein also, we can do very similar things because we've played around sufficiently with some of the other parameters. And in terms of this development, a pilot scale unit, of course, works wonders. And the 2040 unit that we have, 20 mm diameter and L by D of 40, which means 800 mm length. It allows us to work with small quantities, 2-3 kgs, and be able to, so very little. The experiments don't cost much. Otherwise, the cost of protein itself is a killer for experiments. Right? Any study should evaluate the influence of ingredient composition on final product characteristics of meat analogs, microstructure generation, and rheological properties using rheometers. So with this, I hand over to Abdul. I'll stop my share. And Abdul, you want to take over?
Yes, I will take it.
Yeah.
So we'll go to the next part of the demo session where we can see how to run an high moisture extrusion process, and after that I will be showing another process which is low moisture extrusion for making TVPs. So first we switch on the extruder. There is a monitor to set up and configure the extruder, like the bringing the temperatures or thermocouples in, and configuring the temperatures at different zones. And after that, you just insert your application parameters, and then be ready to go. So this is the volumetric feeder which goes in the first port at 0D, and this is the feeder controller unit, and we are just connecting this feeder to this controller. So we need to input the water also in the second port. For that, we are using a peristatic pump. So we use a tube kind of. So before we just fill up the tube with the water, so that to make sure there should not be any air bubbles or any air gaps. So every time we use this lubricant, a food grade lubricant, and this it goes in the second port. And just tighten with the hand, like smooth tightening. And this is the water circulator, a cold water circulator, which is connected to the die, the cooling die. And we can also use a conveyor belt for proper conveying of the material. So, so I'm bringing this feeder in, and the thermocouples, etc. So before starting the process, we just start at the lower temperatures, maybe up to 90 degrees centigrade or 100 degrees centigrade. Just for the information, you can add some more information like moisture content and some other things like this density, etc. So this is the soya concentrate which I'm adding in the feeder, just setting the moisture level. So we just start at higher moisture level in the beginning at a little bit lower temperature. Once the material comes out of the die, we just increase the moisture and increase the screw speed. So we started at like 300 RPM or 600 RPM, and once the material comes out, then we increase the screw speed to 900 RPM or 1200 RPM. So in the computer, you can have a various parameters in a graph. You have melt temperature, you have the pressure, you have the screw speed, you have the load on the motor, where you can calculate the mechanical energy from that, and you can see how it is fluctuating, the pressure, how it is fluctuating if we increase the screw speed. So you can play around these different kind of parameters and optimize your product. So this is another example. This is for the pea proteins. So this is how the texture looks like. So this is all about high moisture extrusion, and we'll go for the third part, which is extrusion process for dry TVPs. So setting up of the screws and different things will be remain same. Just change from the adapter position. We have to add another two heating zones. One is with the heating tape, which is a fifth heating zone, which is connected to the extruder. And this is the round die head used instead of the cooling die head. And this is has a heating element into it. So that becomes a total of 6 heating zones. Same like what we used in the high moisture, we connect a pressure transducer and a thermocouple at the screw tip position. And a bursting pin. So we can connect another thermocouple or another transducer in the die position. This overall process is you can call it as a hot extrusion process, where within the barrel you have very high pressure in that when compared to your high moisture extrusion. So here you can expect a pressure of around 40 to 50 bars. That's how the material which is coming out will be puffed. So we'll be connecting the thermocouples. And another thermocouple for recording the temperature at this die zone. So this is another kind of thermocouple we call it as a control thermocouple to measure the 6th heating zone temperature. So I'll be using a 3 mm round die, which is a very small opening. That's why it creates a lot of pressure inside the barrel. So the can connections. So here I'm using another controller unit, which is a feeding control unit. That's why I'm connecting a series with the feeder controller unit with the cutter controller unit. So additional element here is a cutter. This is the cutting device. So we need to make sure there should be a proper minimum distance between the die and the cutting blade. So here I'm again using the soya concentrate as a feed material. So we need to configure it according to this process. So I have bring in the cutter and other measuring elements such as thermocouples and pressure transducers. And again, we started at a low temperature, 90 degrees centigrade. And again, once the material comes out, then we increase the temperature to the desired level. Again, some filling up this, some informations about the material and the process. So this is how it comes out the material in the beginning. So when the material comes out, then you can increase slowly the RPM and the temperature. This is how the material is cutted into granular shape or elongated shape. This is how the picture where you can have a detailed analysis. This is a dry TVP, a granular TVP. So this part ends here. Any questions? Anything to ask?
Yeah, any questions, keep sharing on the chat session. Otherwise, I will pick up from here. Abdul, you can hear me?
Yes, I can hear you.
Okay, so I'll continue from here. Yeah. Go to the
Okay.
next slide. And okay, so we probably have another about half an hour of slides left. So 1:30, and then we'll break for lunch for about half an hour, and then 2 o'clock we will connect back. Yeah. So just a couple of quick examples of things, kind of experiments. No? So this is an experiment from literature that I picked up, where they're looking at how do you evaluate an experiment. How do you start designing an experiment and evaluating an experiment? So here, looking at two proteins, hemp protein and soy protein mixture, and looking at how do you evaluate what is coming out. So feed composition, they've looked at hemp protein concentration from 0 up to 60%. The remaining is soy. So hemp is 0, which means 100% soy. Then 20% hemp, 80% soy, 40 hemp, 60 soy, and 60 hemp and 40 soy, right? So those are the 4 that they've looked at. And you have to, so that's the composition first part. First part, you have to look at, play around with composition. Second, you have to start looking at temperature zones in the barrel, right? 40, 60, 80, 100, they're looking at HMMA kind of process. So 100 tak hi gaye hain in the barrel. Target moisture, playing around with 60, 65, 70, 75% moisture, and screw speeds changing from 300 to 800 RPM, right? So the solid dosing will change. The mixture was pushed through this long. There were certain dimension of the die, 25 mm, 7 mm, 300 mm, and cooling water is injected. So what was the result coming out was hemp protein. They found out best quality that they, from these experiments, that hemp protein screw speed of 800 produced the acceptable HMMA products. This is a lab-based experiment, so it's not consumer work, but they found acceptable texturization happening, right? At about 800 mm for the hemp protein, and for soy protein, isolate alone, right, which is the first one when 0% hemp and 100%, but only able to extrude soy protein using 500 RPM at 70%, 75% target moisture levels, right? So they came up with a first rough playing around required to just understand what is the zone in which you can play with pure protein, and once you have mixtures in there. So that becomes a very important part. It's a qualitative part, but that's the first part that you have to deal with, right? When you get your materials, even before you start playing, you need to understand the moisture part, right? Your feeding part and your moisture addition. It's important that your powders itself, you are measuring the moisture. So for example, soy protein isolate about 6.39% moisture, but the hemp protein was about 8% moisture. So when you are making different ratios, the starting moisture is different, and that needs to enter into your calculation when you're adding your fresh water into it, right? So that's an important part. Seems like a trivial part, but that's important. We also look at size distribution. So we have a size analyzer. Whatever powders that we get, we do a full size distribution as well, right? For those powders, so that from batch to batch, we understand these material properties, their moisture, their size distribution, the protein composition, the protein content of them, because that is what is important for consistency. And then you get into viscosity, pasting properties. If there is a two pieces of equipment, high-end equipment, which we do not have, but if anybody has access, and most protein companies, extraction companies will probably have that, is some kind of a viscometer to understand the pasting properties of their proteins, right? And also the melt properties of the protein through a differential scanning calorimeter. So those are two additional pieces of kits which are always useful. So I put them in there. What we are playing around with is this kind of a unit, which is a texture analyzer, which helps us understand the texture, the hardness of a material. Some words, hardness, springiness, resilience, and chewiness, are 4 words which are standardized words used in the texture analysis. This machine doesn't just do the standard texture analysis, but can also do cutting analysis, etc. So it simulates our natural biting action of our teeth, right? And then quantifies things. So it's almost like 40 years of research which has happened to come up with these kind of refined instruments. And we have one such instrument in our lab temporarily, as we put together an order and see if we can place an order and procure one. And Abdul was playing around with it yesterday night and trying to compare some of the materials that we are producing versus chicken. So he had got roast chicken and boiled chicken and our own protein, texturized proteins, and seeing how we are differing from materials which are there in terms of these parameters. The hardness, which is a measure of how hard the product is, right? By pressing it. So it's basically a press test, right? What's the maximum force of the first compression? Usually our biting action is a double bite action, which is, we don't realize it. And this also does that double bite action. So first compression then goes up and comes back a second time, right? Because the food is compressed a little and then compressed the second time. So hardness is the first compression. Springiness shows how well the product returns to original structure after the first compression. That's called springiness. Resilience is how well the product regains its original height after the first compression. And chewiness shows how much work is needed to chew the product to achieve the texture that is suitable for ingestion, right? Somewhere those kind of definitions. I'm not putting the exact definitions, technical definitions here. But then also you can have cutting analysis and tensile analysis besides that compression analysis, right? And the tool we have, we are trying all sorts of cutting analysis in our meats to understand how they compare with chicken, for example. And then tensile analysis, stretching and seeing how they breaks, right? The compression is how you press it down, and then cutting is cutting through our incisors, for example. And then tensile is stretching and breaking it, pulling it apart. So for cutting tests, again, we need to, the results are really different, whether you're cutting along the fibers or across the fibers. So transverse or longitudinal fibers. And so there is a preparation of the sample before you test, which becomes extremely important. And for tensile strength also, making so standardized samples is an extremely important part of both these cutting tests and tensile strength, even more than compression tests, right? So that was just a hint about texture analysis. And we are planning a workshop. Hopefully next workshop we will have some more idea about, we'll put in some more content around the texture analysis part. Today we have more on the process parameters as opposed to the texture analysis. Product analysis, one more important parameter that we have in our lab is this colorimeter, Minolta CR400 colorimeter, which allows us to measure the color of the meats coming out. And it gives us in a space, in a color space, which is called the CIA. It's an international color space, and where you have 3 parameters, L star, A star, and B star: lightness, redness, yellowness. For those of you coming from the food industry will be very familiar with this color space, right? And the appearance is also extremely important. And if possible, you could have set up a photo box and take camera images as well, right? So that kind of, and today photo boxes are very cheap and cameras are also very affordable. We will do that part. Here is another example, a little more interesting than the first one, right? Where taking 2 protein sources, soy protein, a blend of 2 proteins, soy protein concentrate and a wheat gluten, right? And mixing them together. 100% soy, 0% wheat gluten, 70% soy, 30% wheat gluten, and 0% soy and 100% wheat gluten. And seeing what happens, right? If to these mixes, what do we do? And how do you observe what is coming out? For those of you who are beginning to do those studies, well, first, the most important, of course, is a visual observation, as we say. And typical characteristic of a meat analog: fibrousness, anisotropy, right? Are we getting those parabolic structures? How close they are? You can actually measure those with the scale and see whether they are narrow and whether the fibers are transverse or longitudinal. So that visual is extremely important. No matter how fancy gadgets that you may have for measuring things, visual is still an expert visual examination is of immense high value, right? Of course, if you're very expensive gadgets, you can go to a scanning electron microscope and actually get the fiber structures as well, right? They're more theoretical and high-end labs rather than for innovation and at the level where we are today. The pictures, you can see SEM pictures on the right side, the gray image of the microstructure SEM. That's the kind of visualization that you start getting at the micro level, right? Which becomes useful, but that's for way later, not for initial starting up. Right? So visual characterization, macro structure, to pata chali jata hai, right? Very easily. There is besides visual, there is also haptic analysis, right? Which is that you put it in your mouth and see what happens, right? So the samples, and you comment on things like what is chewiness, what is hardness. If you can come up with a standardized lingo for describing texture in the small team that you will create, right? And see that, hey, what does, so, and you can come to us to help develop that lingo for you if you want to, that how do we say what is hardness, what is chewiness, what is resilience, small differences between them, but they become extremely important in understanding the whole describing something, right? So here, for example, playing around with texture, how hard something is, how elastic something is. So wheat gluten, for example, is very elastic and very chewy, right? When you have only wheat gluten. Whereas if you have just soy in there, it is very hard, very brittle, very hard structure that it creates. And what we want is somewhere in between. We don't want extremely elastic. We don't want extremely brittle or hard as well. And so that's where you start playing around with wheat, gluten, and soy. And there are so many papers that you will see playing around with these. And we also play around with these two primarily in our laboratories. A lot of our experiences with soy and protein mix and wheat gluten mixtures, right? So that's the haptic analysis, where you put some stuff in your mouth and you can start getting an idea about, even with your finger, right? Basically haptic is touching ke saath, so finger ke saath bhi you get a good idea about all these things. Then visual appearance, as I said, color becomes important, but the appearance of all extruded samples derives from the presence of this multiphasic part that we said, is what is contributing to this visual and haptic experience, which is the how stretched your dispersed phases within a continuous phase, how well mixed these phases are. A dispersed phase could be observed, which is oriented in flow direction. You can observe those transitions, for example, right? And it is that meat analogs contain 20 to 30% of wheat gluten, for example, are close to the texture of boiled chicken meat, was the conclusion in this study. We get closer to 15 to 20, we've got very good results, right? 10% maybe we've got good results actually, right? And we're looking at higher incorporation, say kya hota hai. Wheat gluten, interestingly, will also give you lighter color products, more chicken kind of products, right? As opposed to only soy will give you darker products. So, okay. These are some other really fancy tests that you can do. Rheological tests. We don't have a rheometer here, but if you have access to a rheometer, then certainly some oscillatory tests can be done, right? Which are not possible on texture analyzers, right? And so rheometers become, because you can keep changing your rotation, you can oscillate it, the force that you are applying. And that becomes the frequency sweep, gives you an added level of information. But overall, this is what a rheometer will tell you. It gives you a stress strain diagram, and where on the y-axis you have the force applied or the stress, and the x-axis you have the strain, how much material has stretched. So if it is a flat curve like the red one, it has stretched a lot with minimal force. Whereas the black one is hardly stretching. You require a lot of force to stretch it at the same level. And so the black one is way harder because a lot more force is required to stretch it. Whereas the red one, minimal forces stretch ho jata hai, so it is very elastic in that sense. It is softer. So you want somewhere in between, and that 30% mixture of wheat and soy is giving you somewhere in between as expected, right? So that's the young modulus part. That's the rheology part that people will talk about. But that's what you're also looking at, hardness versus stretchiness, right? Kitna hai. So between these analysis, if you're just looking at soy, for example, yes, you get, no matter which of these three products you had, whether you had only soy or only wheat or a mixture of the two, you did get a fibration in all three of them. So anisotropic, you have a green tick for all of them, right? But if you're looking for only soy, it is very hard and brittle. If you're looking for wheat, it is only chewy. So a soft, desirable chewiness is somewhere in between that you get. You don't get from pure products, which is one reason why you're going to blending as an example. So what are the process variables that you can play with? We mentioned the length and diameter of the machine, but that's fixed now once you bought it. We said it should be long enough, right? L/D ratio should be long enough so that it spends enough residence time. Abdul also showed you various configurations, the low shear, high shear configurations by putting together the various shear elements. So that's certainly another element that we play around with in our experiments. We have low shear configurations and we have high shear configurations that we play around with, depending on how many kneading blocks that you put in, how many reverse elements that you put in, right? So we can play around with those. And then the die texturization, the die shape, we have 2 dies for proteins and a lot of others, some 6, 7 dies others for starches that we play around with. And then the heating zone. So those are, of course, the capital part of it, which is the equipment part, parameters that you play with. And then you have the process variables that you can alter with the same set. Temperature is the primary one here, right? And so the heating zones, the 2 that we have in the middle one, the hot extrusion, the high moisture extrusion, are the 2 that we use largely for our starting zones for the 2 products. The middle one, the hot extrusion one, is for the low moisture product, dry protein, and the high moisture is the bottom one. Both of them beginning at around 40, but here we end at about 130. The hot extrusion, we go about till 160 or so. Soy usually 120 will do for an HMMA product, and pea about 140 will do, pea protein. The feed rate is another impact. Water absorption, torque will be higher, die pressure which is generated is higher, so there's a bigger drop across the die, more puffing can happen as a result. There is a change in color with feeding rate as a result of all these things, darker materials, and water, it becomes lighter as you feed more, lesser time, and water solubility index, absorption is higher, but soluble materials are lower, right, as such. Screw speed is another parameter, immediately changes the amount of mechanical energy that you're putting in. That's the easiest way to put in mechanical energy is through screw speed. And raw material composition, of course, has impact on viscosity of and the moisture of the material, the chemical composition of the that you have that brings in. So raw material composition may impact many of these things as well. Water and steam addition, you can see 3 products that we had about water addition, 65%, 67.5, and 70% moisture. And you may say this is small amount of water change, but has massive effect on the product attributes that when we check them. And feed moisture as it goes up impacts density and also impacts color. So you can play around with not just the fibration and the strength of the fibration and the length of the fibers, but also color impact is also there because of water. What you can monitor: pressure, you can monitor temperature, you can monitor motor load, you can monitor. And so Abdul in his videos showed you various places for attaching all the thermocouples in the extruder section, and also emphasized capturing the temperature in the die section as material comes out. And they become very important to control and also to monitor to make sure that the process is running very consistently. Right? And so overall, you can make, therefore, a experimental sheet when you are looking at designing experiments at the pilot scale. You come up with, let's say, we have 2 screw configurations, a low shear configuration and high shear configuration. So 8 experiments for low shear and high shear. Within the low shear configuration, then 4 experiments at low RPM, 200, 4 experiments at higher RPM, 400 RPM, right? So that then further dividing into the rate 540 grams per hour feed rate versus 960 grams per hour, right, of feed rate. So you've changed the feed rate to per each. And then extrusion temperature, you can have 80 degrees centigrade and 180. So you can see that by mixing and matching, you've created of these 4 parameters itself, you've created 16 experiments that you can create. And then you can monitor the melt temperature, TM, the pressure, right, and the other parameters, residence time, etc., that you can monitor, whatever. So that's how a experimental plan would look like. You will create it on paper depending on what is required. We would put that on paper and then run those experiments over 2-3 days, right? This is probably 3 days of experiments that will require. And what comes as an output, simple output here, for example, is, I mean, just showing some why we play around with these things is that you want to control residence time, for example, how much of time material spends in there. And so how should you change residence time? You can change by, we said, increasing screw speed will change the residence time, and increasing feed rate will change residence time, right? And we see that feed rate badaya, to feed rate, high feed rate has higher, in this set of experiments, a higher effect on residence time, that you can see that these experiments, low shear experiments and high 1, 2, 3, 4, for example, you're seeing, then the difference between 3 and 4 is screw speed, but the difference between 1 and 3 is that of feed rate at the same screw speed. So feed rate has created a much more difference in residence time compared to the feed rate. That's why the conclusion here. So that's one way of taking care of residence time. The extrusion temperature has hardly any effect on the residence time. So you can play around with it without changing residence time. Different screw configurations, high shear, low shear, seem to have hardly any effect, right? Your 1 and 9 are very little different at height, both of them close to 100 seconds of residence time, very small difference, right? So those parameters don't seem to have that much of a residence time. So now we know that when we change temperatures and screw configuration, we are not impacting residence time, whereas screw speed and feed rate are impacting residence time in a much bigger way, right? So that's what gives us an idea as to what's happening in an experiment, right? Sample temperature, for example, temperature coming out, increased with higher extruder temperature. So of course, the moment the extruder temperature badega, the sample temperature increases. Increases with screw speed. If you have a higher screw speed, more energy going in there, and sample temperature increases. Different screw configurations seem to have lesser effect on the sample temperature. So high and low shear doesn't seem to have that much of an impact. The speed had a higher impact, right? That's something we learned. Extruder torque, how much of torque I'm putting in, increases with how much of energy I'm putting into my mechanical energy, increases with high shear configuration. The more the shear configuration, even at the same RPM, if I have a high shear configuration, it's increasing my torque going in, right? Torque is also higher at low temperatures. If I have my barrel temperature lower, at the same RPM, I'm trying to maintain my torque energy going in there is higher, right? Because the melt is still very viscous, right? Higher feed rates with the same screw speed generates a higher torque, right? So I don't need to change RPM, etc. by feeding more, which means that my feed at the same, I'm probably running empty barrel in my first experiment, and now I have filled the barrel. That creates a lot more torque. And then increasing the screw speed decreases the torque because वो melt हो जाएगा, temperature बढ़ जाएगा, and then it moves things easily. Sample viscosity that we are looking at, similar results, highest sample viscosity for this set of experiments, 120 degrees centigrade. The test results integrate that extrusion with a low shear screw configuration at 120 degrees as opposed to 80 degrees, gives us the highest feed rate, and the higher feed rate delivered the best gelation. So you can play around with sample viscosity as well by playing around with some of these parameters. So playing around with sample viscosity, playing around with residence time, playing around with torque is what we are trying to do when we are changing the parameters that we can change, right? Which is RPM, which is feed rate, which is temperature profile. Those are the parameters we set, and they are helping us adjust the residence time and the torque and the viscosity of the product and the mixing that we achieve, right? So as we go from plant proteins to meat analogs, how do you create the organoleptics? We said fibration is the key. We are creating fibers, but there are additional steps that you could do, right? You could create color changes by adding more colorants. You could create fats, add fats to it. You can create a whole second set of culinary parts that we'll talk about very briefly. So primary processing in a dry TVP product, you've generally processed using low moisture twin screw extruder. You've composed of pre-combined ingredients. Everything is already in there, and you've extruded. It does not generally include too much of fat in the primary extrusion. Post-extrusion passed through a dryer package and sold as dried product after drying, low moisture, right? And it's stable. Wet, sorry. Resume share, yep. So wet process, generally processed using high moisture twin screw extruder. Moisture level is about 65% and above. No dryer at the end of extrusion. Incorporation of fats is along with all the dry ingredients, right? And we can add it anywhere between the first, second, third stage, right? Final product has higher moisture. Additional steps of marination and coating are generally required in the wet process. Yeah. Oops. Yep. In the dry TVP, once you open the pack and you want to use it, you have to do hydration first, right? With water or broth, whatever broth you use, vegetable broth or non-veg broth, chicken broth, etc. So you have to hydrate in a broth. And then post hydration, you need to do marination, incorporate fats, flavors, etc. In a wet TVP process, likely that fat is already incorporated, some amount of fat is already there. And but if you're converting into patty, etc., you can add further fat. And marination, certainly that you can do. Wet TVP, additional productization done to incorporate additional flavors, can be multi-step process because you can have exterior coatings of spices, flowers, breadcrumbs, etc. You can do multiple processes. So number of such. What are these wet TVP additional processes? You can do cooking, for example, reheating everything, frying, baking, boiling, steaming. You could also do extended shelf life processing, such as retorting is done, heat pasteurization is done, UV is done, right? You could do various things, combinations of these to stabilize this because it's a wet product. And then finally, refrigeration, freezing, or a combination of these. The number of market products very quickly, right? The first thing that I just wanted to leave that thought with you that we may never exactly be able to. Don't come expecting. We shouldn't expect that we are matching a chicken or a beef exactly, right? We are getting into a texturized space. We are getting into similar textural and color properties and taste properties, but it is a new product in some sense which is getting created, right? So it adds to the complexity of the product. So also that we can add complexity in other ways as well by adding sauces and battered products, right? And increase the wow factor through the culinary part. Don't ignore that part. That's an equally important part. Well, we are not covering that in this workshop. That's maybe for another day that we'll have a workshop on the culinary part of protein. Then bulk pack meat alternatives, etc. That it's not just mince meat, but we're looking at bulk, or not just granules, but we're looking at bulk like sausages and patties, etc. as well, right? So, and for the final formulation, we are proteins, while our focus is on protein texturization, starches and fibers and other additives also play some role in there. Like, so fillers, for example, most frequent protein fractions, oil seed, cereal grains, etc. They improve flexibility in the dough, right? Can help in incorporating a little bit of air bubbles in there. The plasticizers, such as water and oils and fats and emulsifiers are used. They influence the flowing of the whole material, right? They reduce degradation of proteins and can impact positively some of the nutritional elements like vitamins, etc. in there. The hydrocolloids are thickeners that we are used, like stabilizers, etc. They modify the texture, right? Xanthan gum, guar gum, locust bean gum, they are used. Maybe more in starchy products as opposed to protein products, but there is a room to play with these things. And emulsifiers, of course, to make sure that fat and proteins don't separate out, right? And they facilitate shear and formation of uniform extrudates and balancing of the phase behavior of the dispersed phase and the continuous phase. Soy lecithin, monodiglyceride esters, etc. are commonly used emulsifiers that you come across. And then baking powder is always an interesting, I really find baking powder is a very interesting material to try in foods, because it gives, primary purpose was to raise flour, for example, right, to create carbon dioxide and create bubbles in there. But also it creates crispiness, creates brownness. There's so many other uses that we have found of baking powder. Interesting to try in there. We haven't tried this yet, but I put it there because I thought it's another interesting series of experiments to do. Certainly not the first experiment, but worth exploring. And then taste components, of course, salt, sugar, flavorings to improve color, taste. Some products in the market you've seen, Beyond Meat, a very popular one, and Siddharth will also cover maybe some of this in his presentation. I hope Siddharth is on. I don't know whether he's on or not. Hi, Siddharth, in case you're on. Yeah.
Hi, Dr. Gurmeet.
Hi, Siddharth. Yeah. So Beyond Meat was one of the first, right, which created a lot of this buzz a few years ago. Uses pre-protein isolates was their initial forte. Coconut oil, as I said, is they're focusing on plant meats, right? Minced meats product was the main category to address initially. So burgers, meatballs, sausages, and coconut oil is frozen at room temperature, and therefore creates a fat layer like meats have, and when you heat it, it melts and creates a very good taste and texture and look and feel of it. And then certainly trace minerals and carbohydrates and water and beet juice. They use beet juice for color. Chicken, of course, doesn't require that much of color incorporation, right? But other meats do. Impossible Foods is making waves again. They started off with a mix of soy proteins and wheat proteins, but have shifted entirely to soy proteins, right? Because wheat gluten allergy, a lot of people have. Some people have, so they moved entirely to a soy platform. Have a little bit of potato protein, appears way down in their list. Coconut oil again, primary oil, and then sunflower a little bit. Natural flavors, hydrocolloids. They use thickeners, they use emulsifiers, they use minerals, and they use a very interesting ingredient called soy leg hemoglobin, which gives the taste and the color of what hemoglobin would do in normal meat, right? It's a heme, it's a vegetarian heme found in the roots of soy, but they do it through a fermentation process by having taken that gene and put it into a microbe and now culture it and produce that. So if you are a techie, you would be awed by a food techie, you'd be awed by all this. Nestle also has awesome burgers, and pretty much every big company today now is into texturized vegetarian protein, which is why I say that this is no longer a fad, which it was a few years ago. It has become mainstream now, right? And it has a future. And when it has a future, it's time to start investing into it. Kraft Foods, another big company, right, with their Boca range of meatless patties. They use, again, soy protein concentrates and isolates. Hydrolyzed soy proteins for some taste. Good Catch Foods focuses on the tuna analogs, and they claim to use these novel legume proteins like lentil and navy bean and chickpea along with soy protein to create their textures. New Fave Foods is on plant shrimp alternatives, and they use seaweeds to create that kind of a flavor and soy protein. So seaweed and soy proteins and natural flavorings. No Evil Foods, plant-based chicken, wheat gluten. Wheat seems to give the most chickeny kind of, so wheat and soy mixture. So wheat almost seems very whenever we try and work with chicken, wheat gluten comes in. Of course, the issue is of gluten there. But then the red kidney beans and chickpea flour are other successes they got with here. And then Mondenison with their Quorn range, which is cooked from scratch, and mycoproteins is something that they use, right? The fungal proteins. So understanding a label, one of my last slides here, right, which is they have taken I think Impossible Burger ka labeling tha, and looked at all the ingredients. You'll see that here's such a number of ingredients here, right? So they use texturized proteins as one ingredient, but then so many other ingredients. So you have water as the number one ingredient in there. If I add up, for example, I go through this labeling and say, for 113 grams of product, I have 14 grams of fat. I have 9 grams of carb, that is 14 plus 9 is 23. And I have 19 grams of protein, that's total 42, right? So total 42 ho gaya, grams of stuff in there, and then maybe a few milligrams of other stuff out of 113, right? So which is nearly 60% is water in there, right, in this product. So then soy protein is part of that 19 grams of protein, right? And then you have coconut oil. Coconut oil and sunflower oil, between the two, are contributing that 14 grams in this list. And of course, coconut oil appears first, which means that's the majority of the fat in there. Natural flavors, 2% or less, right? And so all the other ingredients are probably lower than that. So potato protein is there, but probably less than 2%. Methyl cellulose is a thickener, yeah, that we are using. Hydrocolloid, it's a thickener. It thickens things, holds it together, holds the patty together. Yeast concentrate is usually used for flavoring, right? That's what I use. Yeast concentrate wherever I've used is for flavoring. The yeast is used in biscuits, not just for raising, but for giving the biscuity flavor. Dextrose is a sugar source in there. Food starch, creating a little bit of gelatinization in your material, flowing characteristics. It's a filler, it's a binder. Modified soy leg hemoglobin is the equivalent of blood that you are putting in there, but it's a vegetarian. It has the touch and feel, the color and the taste, the metallic taste that you would have from a non-veg food. So the Beyond Burger, while that uses beet color, this one uses leg hemoglobin. Salt to taste, soy protein isolate is another, but only in small bits that they've added, right? It's way down in the ingredient list. And then all the other additives, mixed tocopherols is vitamin E. Sodium ascorbate also is there, which is vitamin C. Now, tocopherols, vitamin E and vitamin C, both of them are also antioxidants. There are a lot of questions about stability of these. And these two things added in there are creating, probably not for fortification. Vitamin C certainly will disappear with time, right? They are probably there for making sure that there are antioxidants, so the fat doesn't become rancid in there, because you're adding coconut oil, right? It can, over a year, it can become rancid. So you need to add some antioxidants. The vitamin B6, vitamin B2, zinc, thiamine, vitamin B12, they are all added, probably they are added as fortificants to bring the overall composition closer to that of meat. So now that's the way you construct recipe from ingredients. And so overall summary, Twin Screw extruders offer a unique, innovative method to transform protein-rich ingredients, right, globular ingredients, into very well-balanced fibrated proteins. Now we are creating a new texture in there. Then the expertise and the process know-how are key points, however, to convert a non-fibrous protein into a protein, a textured protein. The new generations of meat analogs are showing higher conversion efficiency and better environmental impact compared to traditional meat products. So big environmental reason. And with knowledge and know-how, taste can also be conquered. And they offer the opportunity to address this whole new trend towards flexitarianism, but also creating a new range of tasty products, right? And protein fibration technology appears to be one possible key sustainable solution to feed these 2 billion worldwide consumers, right? Rather than having them take up non-veg because there was no choice. So overall, understand your ingredients. Hopefully what you have learned is we need to understand our ingredients very well before we start working with them in our extruder. We need to set up our extruder to optimize process, and there are a number of parameters and variables that we need to play around with. And only on a small scale we can do that. So start at a small scale, start at a lab scale is what we would suggest. Do as much of monitoring of extrusion variables as possible. So when you get your reports, make sure you're getting a lot of parameters in there. And then check for texture, color, taste, and other product attributes you have interest in. And have patience, right? Somebody said, how many trials? He said, well, in three days of work, you can get to very reasonable, good quality products. But then it depends on how much of patience you have, and getting to a perfect product is always requires patience, right? We have another upcoming workshop, 24th, 25th, 26th, most likely. We'll confirm the dates, but that's a 3-day hands-on workshop in the pilot plant, where you'll actually get to do many of these things or see these things happen right in front of you in the pilot plant. So hope to see some of you there, and do spread the message to others who may be interested. Yeah. And yeah, come to our laboratory. A little bit of publicity. That we have a good unit, some expertise that we have developed, and we welcome students, UG, PG students to do internships, projects, PhD students to come and create a project here. And of course, training programs that I just mentioned. So more than welcome to join. And hopefully you had a good first session with us. These are our contact details. Do get in touch with Abdul if you need any further clarity on any of these charts, ingredients, etc., or have any questions. We have Siddharth on the call, and we have Maria who will be joining from Brabender. Siddharth is from Good Foods Institute, an expert, and he will be leading the session in the afternoon. I think 2 o'clock Maria will join in. I'm giving you very little time for lunch, having overrun as usual. So I'll break immediately, and 20 or so minutes for lunch.
Will we be getting the presentation copy?
Yes, you will all get presentations from Abdul. Cool.
Thank you, sir. Thank you. Thanks for your nice coaching, sir. Thank you.
Thank you. Bye-bye. See you. I'll be logged on, but we meet after lunch. Yeah.
Yes, sir. Thank you. Please.
Is what happening to the proteins during the extrusion process. So when we talk about proteins, the first thing that comes in mind is denaturation, of course, when we're talking about high temperatures. So the goal during the extrusion in the extrude section is to denaturize the proteins. So depending on the protein, of course, we have different denaturation temperatures, but what is happening for proteins when we are heating up the system is we have the native protein. Usually the proteins, they have a globular structure. So when we heat up the system, this globular structure is destroyed. So we have like unfolding from the protein molecules. And during this unfolding step, we have binds or bonds that are being available for reaction. We have several reactions that can take place. For example, you see here binding, in this case, through disulfide bonding, or of course non-covalent bonding. But that's a little bit maybe too in detail. Just take in mind that the proteins are able to denature when we have higher temperatures. So, and why is this important? Because when we're talking about high moisture extrusion and meat analogues, the question is, what about the texture? Because the goal is to achieve a product that is similar to meat. That's why we call them meat analogues. So, yeah, here you have in the, I don't know if you can see my mouse, but here you have like a description or graphically describe what's happening during the cooling die. So we have this protein carbohydrate melt that has like high temperatures and is cooling down. So we have a transition between a liquid to a more solid material. Here below you see how can the product look like after the cooling die, and you see it's actually like a solid. For meat analogues, to the products to achieve this meat-like texture, there are different theories that have been presented in the last, I think, couple of years. The first of one here described recently, but it's an adaptation from a really old publication, is by Liu and I cannot I cannot say that right, but I think Hesier, I don't know, maybe in year 2007, they described that the reason that the meat analogues achieve this kind of texture is due to the fact that the proteins that are being denatured in the extrude section unfold and align during the cooling die and in direction of the flow. So this kind of textures that we see are actually the how you call it, the fluid dynamics, like shear, due to the different shear velocities, the material is taking this form. So to put it in a more simple way, that's one of the theories. The second one is a little bit older, from Tolsogusov. There's actually, he is a food physicist that has been from Russia, that has been working in the field of foods and polymers a long time. And the theory he proposed is that we are talking about, of course, multiphasic systems. Multiphases in this case are because we have the water, we have the protein, and we have the rest of the materials in the present in our mixture. So because we have different materials that react differently to temperature and shear, we're talking about a multi-phase system. So, and because we have the materials that react also different, they can phase separate. Phase separate in this means a different things. Also, you can understand it this way. So you have this protein melt that firstly you have denaturation, but depending on the processing condition, of course, not all of the proteins in this case are going to be denaturing and due to the fact that aggregating. So we have then a difference. So when you have this difference, it can be that due to the different properties of these systems, then you have like phase separation. And due to the phase separation, you will achieve these mid-like textures. And a more recent theory is from Holland. Ms. Dekkers proposed that this texturization of proteins is actually as a result of only air bubbles, because depending on your cooling die and the temperatures, you will have like expansion. Of course, for high moisture extrusion, you don't want expansion, because then you won't get the meat-like texture. But you cannot like avoid this completely. So they took the final products, just as them here shown in the picture on the left underside, and they did some microscopic picture of them, and then found out that they had like air bubbles. So although extrusion in this case and protein texturization using extrusion processing has been a long time, and a lot of research work has been done, you see the idea or the reason why we achieve such textures is not unified yet. Maybe is it because you have a lot of different processes occurring. Maybe it's because we're talking about a very complex system. Not the extrusion process itself, it's also a complex system, but also the materials we're talking about, from biopolymers in this case, they can also be very complex. Yeah, but nevertheless, we are able to kind of achieve a meat-like structure. And then it's a question, how do we do that? In this case, because we're talking about a case study of lentil protein concentrate, we obtained this material from a company here. And just for you as information, this concentrate has a protein concentration of approximately 56%. So our usually setup for high moisture extrusion is shown here on the right side of the slide, and you can see we have different machines. We have, of course, our extruder. We have the dosing system. We have a peristaltic pump to be able to dose water. We have, of course, our pressure sensor, or a pressure sensor. We have our cooling die, and we have also here shown a conveyor belt. Usually, when we are doing like extrusion trials, we divide or trials in 4 steps. First of all, our starting procedure and or stopping procedure. And then we have, depending on the experience we have with the material, we avoid a parameter determination step and go directly to sample production. But if we're talking about a material that we are not so experienced, we of course have to first get to know the material, know how it is behaving during the extrusion process, and then when we achieve the optimal conditions, we can like get our samples from them. But usually you will see here in the starting procedure, we have low shear and low heat. So you see that our screw speed is at set it up 80 reps per minute. Moisture content of the material is being set up to 65%, so we have more of a like a solution. And our temperature profile, here you see heating zones 1 to 5. In our extruders, you can heat up every zone differently if you like. So here we have the 40, 60, 80, 100 temperature profile, and our cooling down was set to 30 degrees. Then, of course, if we're talking about preparation or production of meat analogs, we have to, like I mentioned, be sure that our proteins are also denaturing. So that's why we increase them, the shear and the temperature stepwise. In this case, we increase our screw speed from 80 up to 1,200 reps per minute. That's the maximum that our extruder offers. We change the moisture content between 65 and 55, depending on the material. And then, of course, we go up with the temperature up to 140 in the last elements before the cooling line. And then here I show you for, in this case specifically, lentil protein concentrate. We found out that our optimal conditions in this case were a screw speed of 1,200 reps per minute, a moisture content of 57%, and the temperatures were around 110 degrees, and our cooling dial was set up at 50. When we are done with the experiments and we want to clean up the extruder, of course, we go back to the low shear and low heat and increase, of course, the moisture. And in this case, we allow the extruder to clean itself because we have the two screws that are rotating in the same direction. So they are taking then the material that has been accumulated by their own. So here a little bit of an input how our products, and depending on the, of course, processing conditions and setup conditions, the material is looking up. Like I mentioned at the starting procedure where we have low temperatures and low shear, the system looks more like a suspension or like a really thin dough. Then if we go to the parameter determination step, where we are increasing the temperature and shear, we see you can get two sides. One, if you are a little bit hesitant and set up the temperature not high enough, you have a product that is undercooked and will look like similar to what is shown here. And if you go like too high up the temperature, you will get the other case. So this, in this case, an overcooked product that will like this. So the optimal conditions are usually something in between. And look, like you can see in the next pictures, you see in this case a product that has a really nice fibrous structure that in some way is similar to meat. And in the last step, when we already had a product that has been extruded like with the optimal conditions and we are happy with the results, then we increase again the water, and then you see again like a thinly or like a thin dough that is being extruded. So that's about high moisture. I hope this worked. I wanted to give you a small video to see what can happen if you set your cooling die not at the right temperatures. Hopefully it works and you can see it. If your cooling die has a temperature that is too high, you will see that you will get expansion like you see in this video. So expansion was something that we did not want to have when we are doing high moisture, because as you see or you saw from the video, the texture is not even similar to like a meat or piece of chicken, or I don't know, something similar would look like. It's more like a doughy, at a doughy texture. But nevertheless, expanded products are also something that we produce. And in this case, usually when we want expanded meat analog, we don't use a cooling die, but we use a short die. So it's very similar. In this case, low moisture extrusion, because low moisture is the in principle, you need low moisture, so you have expansion after the die. So the protein and water concentration are a little bit different than high moisture. You have usually protein concentration above 60%, and in this case, water below 40%. The extrusion is set at similarly at temperatures above 100 degrees. And like I mentioned, you don't have, or we don't set then a cooling die, but a short die to let the product expand. So what is an expansion? Expansion usually occurs when you have temperature and pressure gradients between your die conditions and your room conditions. So here you can see in this graphic what's happening. You have your die, your material, your protein melt in this case. Then if you have the chosen or the correct conditions, the protein melt will in this case expand. You have puffing, collapse, and setting. And of course, this is a time-dependent process, and of course, also depends on the conditions in the die. So why? Because like I mentioned, for expansion, you have different influencing factors. Of course, the geometry of your die. You have the conditions before and after the die. In this case, usually the temperature and pressure gradient. And you have the material properties. So why are the material properties so different, so important? And why is the temperature also so important? Because you know expansions occurs when the vapor, when the pressure is below the vapor pressure of water. So here you can see a pressure versus die length diagram for two types of materials, as a 1 and 2 in this case. Material 1 has a higher viscosity than material 2. So depending of the viscosity and the die length, the pressure will be, how you call it, will decrease differently, like you see from the lines. And the point at which the pressure at the die or of your material is below the vapor pressure, then expansion will begin. So if your gradients in this case are gradient temperature and pressure are really big, then the expansion increases. So here you have like a little bit more of theoretical information about expansion. Yeah, so for low moisture products, you want expansion because usually this kind of meat analogues, they are not, how you call it, they are further processed. So usually, you know, TVP, the textured vegetable protein, is like has like a spongy texture. So this product is expanded, and it has to be how you call it, mixed with water so that it absorbs the water after a predetermined time, and then you can cook it. So these are not final products; they are like you call something like intermediate products. Nevertheless, they don't have this meat-like texture, but for example, chili con carne or stuff like that, you can use these kind of things, because when the expanded product has absorbed the water, it looks more like how you call it, yeah, something like a meat filling that you can use for different products. So for the case study of low moisture extrusion of LPC or lentil protein concentrate, we have a very similar setup. Of course, we have our extruder, we have the dosage system and our pumps. But in this case, we don't have the cooling die, we have a short die, and yeah, the conveyor belt is also present. Yeah, so similar to the already shown results, we have in this case also these 4 steps that we do during our trials: the starting and stopping procedure, that has a low shear and low heat. In this case, we start very similar and end very similar with a really high moisture content, but then we reduce this stepwise. Yes, the temperatures, they are, like I mentioned, all very similar. Also in the screw section, we have temperatures between 40 and 140 degrees, but of course the optimal conditions depend. And in this case, the screw speed for the optimal conditions were 400 reps per minute, moisture content of 45%. Of course, we have tried this also in 35-25%, but for the case of a low moisture expanded meat analog, 45% were gave the better product. And the temperature profile was similarly. In this case, the last heating zone 5, was set up at 90 degrees, because if you set it up higher due to the high viscous dissipation of the material during the extrusion, the actual temperature in the heating zone 5 was above 100 degrees. So if we set it at like 140, then you will have 160, and 160 was too high, and you will see it. You see it here. So when the temperature is too high, and you have of course also higher shear, you will get an overcooked product that look more like a string of, yeah, something not resembling any food stuff, you know. When you have undercooked material, it's more like a dough. You see a little bit of shark skin. I don't know if you know or you know what I mean with shark skin. Shark skin is usually occurs usually when you have in your die, you have material that has been accumulated around the die, but in the middle, because you have another velocity, the material is flowing. And due to the fact that around the die, the material has been in longer contact with the metal and the temperature is high, you have like a different material properties. And you get like a spongy material with hard surfaces. So the optimal conditions, as you see, we get like expanded product. The expanded product can be used for different applications, not only as a meat analog. It can also be as a, for example, snack, can be used as a snack, because you see it's like really expanded and really crunchy. And then if you again go to the stopping procedure, you will see that we have like the higher moisture and the lower shear and shear and heat conditions will result that the protein mat is not cooked and it's only like mixed, and then you will get like a really thin dough. Yeah, so that was for me and my small presentation. We are your partner for product and process development. So if you have any questions, comments, applications that you want to try, you can come to us and we can try your material. And if you have any other questions, I will gladly answer them. And of course, thank you very much for your attention.
Thank you so much, Maria. That was really a nice presentation. I think got some good references and a very nice way of presenting the scheme of how to do trials. No, the starting phase, the experimental parameter determining phase, and then the sample preparation, and then what do you do in closing up. And I think with the right pictures, it makes things so clear. No? So,
yeah, that's why it was not a long presentation, but due to this 4-step division, you can get a lot of information. Also see how is the product development depending on the chosen conditions. Yes.
Yes. Thank you so much.
Yeah. You're welcome. So I got a direct message from Arun. Sorry if I cannot spell your or say your name correctly. Your question was, what is good for culinary, high or low moisture? Yeah, that's a really good question, but I cannot say you directly what is good for culinary because it depends, of course, on the product you want to use. Like I mentioned, high moisture, the goal of high moisture extrusion is to achieve like a done chicken-like texture, for example, chicken or turkey or yeah, something like this. But in construct, low moisture is not to be treated like a done product. It's more like an intermediate product. So everything that has to be mixed and spiced up and maybe filled in some like a noodle or dough material, you can use it because it's that the texture itself is not so important. Yeah, so that's my answer. Hopefully I answer you yeah, correctly.
Maria, any idea what Impossible Burger or Beyond Meat use for their burgers? It's like a low moisture product or a...
Actually, they call it middle moisture. Because the last time, I think it was the last 2 years ago, I was talking with one of the Beyond Burgers guys, and of course they cannot give you a lot of information. And that day, because I was coming from the university still and doing my PhD, where they were more like trying to give information. So they mentioned they for the burgers, they at the beginning they use low moisture, and then they mix it up in like kind of a stand mixer, but it would not hold the texture. Like, you know, sometimes you're making your burgers, you don't have like this binding of the mass, and then it's like fall downs. So of course they have a lot of hydrocolloids mixing in the mixture, but they do something like a middle moisture extrusion that is more about 40-45%. So they have half expansion, half not. It's yeah, something like that.
Okay. Great. Any other questions from the audience?
A freeze product. So Aaron, thank you again for a question. So after extrusion, they process to make a freeze product. Yeah, freezing, that's actually a huge topic because, you know, not only regarding the proteins, the temperatures affect the proteins, but also how you do your freezing. It will affect the texture afterwards. So yeah, they you can also buy, I think in India, at least here in Germany, you can also buy like frozen patties that are vegan, sorry. So yeah, they do it and they freeze it. Yeah, so after extrusion, not directly, they process it, they mix the stuff like the condiments and maybe like some stabilize, how you call it, thickening. And they
Lucid, really nice presentation. Yeah, and thanks a lot. If there are no other questions, we'll move to the last presentation of the day, which is from the Good Foods Institute. Siddharth, are you there?
Hi, Dr. Gurmeet. Can you hear
Hi,
me?
Siddharth. Yes, I can hear you. I think I need to make you co-host. Yeah. Yeah, you are a co-host now and you can present, share your screen. Yeah.
Okay. Second.
Sorry to keep you waiting, Siddharth. Yeah.
Oh, no problem at all, Dr. Gurmeet. This was a very informative session. I've been like hooked since 10 a.m.
Okay, cool.
Okay, perfect. Can you see my screen?
Yes, I can. Yeah.
Okay, sounds good. Give me 1 second. I'm just trying to. Okay, so should I start?
Yeah. So I think just a few words to introduce Siddharth. Siddharth works at the Good Food Institute and is one of the experts there on proteins. And as I mentioned at the start, at around 10 o'clock, 5 hours ago, 6 hours ago, that when we started putting this program together, we had a conversation with Good Food Institute, and we realized that both of us share this interest in taking the knowledge that we are generating out to a wider audience. So we thought we'll come together and create this program. And so this today's workshop is this output of this joint collaboration and the calls that we had and the discussions we had. Siddharth, we're grateful to Siddharth for taking the time out, putting this deck together, and being a part of this workshop. And we hope that we'll have many more such collaborative workshops over the next few months. Yeah. Siddharth, over to you.
Thank you, Dr. Gurmeet. And before I start, also I would like to thank Dr. Gurmeet, Abdul, and the entire team at TDU for putting this really informative workshop together, and also Maria from Brabender for this wonderful presentation, and also to our participants today for this workshop for building this ecosystem. So a little bit about me. My name is Siddharth Bhide. I work as a science and technology specialist with the Good Food Institute India, and on the plant-based side. And I'm a food scientist by training and by experience. So I have my undergrad and master's degrees in food science. And then I've done a couple of internships with Nestle, General Mills, and I've also worked full-time with Just, which is a company based in San Francisco. And I worked on their plant-based tech product before I joined GFI India in July 2019. So the agenda for my presentation today would be I'd be talking about the smart protein sector in India and around the globe, and what exactly the Good Food Institute India does. Then I'll be talking a little bit about plant-based meat, egg, and dairy products. So talking a little bit about the crop optimization part of it, raw material optimization, and then the end product optimization. Then I will be talking about the market for plant-based meat products in India and around the globe. And then in the end, I would be ending with, the initiatives that GFI India has taken to advance the smart protein sector, and how any stakeholder in the system, like all the participants over here attending, how could we build this ecosystem together? So the Good Food Institute India, we are an international network of nonprofits. We are located in 6 countries: the United States, Brazil, India, Europe, Asia Pacific, and Israel. And we have 100 plus employees through the globe. And then we primarily work to accelerate the shift to a sustainable, healthy, and just food system, uh, which is the area of alternative proteins through three key areas of work. The first one is science and technology, and I'm a part of the science and technology team. So here we work to analyze, advance, and fund the foundational science of alternative proteins. We also have a corporate engagement team where we consult with the world's biggest food companies and emerging startups to help them capitalize on opportunities in the alternative protein market. And then the third area is policy, where we advocate for fair regulations for plant-based and cultivated meat through the globe. And as I explain you some of the initiatives that GFI India has taken, I think these would be more clearer with examples. So really the question what we are trying to answer through our work is how do we feed close to 10 billion people by 2050? And Dr. Gurmeet already pointed this out that the world population is increasing and we need to match up to it with regards to our food supply in means that are sustainable, that are efficient, and that are safe. And when we talk about sustainably, we, as Dr. Gurmeet mentioned, is that animal industrialized animal agriculture is one of the top contributors to a lot of environmental issues that we are having, like greenhouse gas emissions, etc. Similarly, animal agriculture is not at all efficient from a calorific conversion standpoint because even the most efficient animal, which is the chicken, takes about 9 calories of input in to produce 1 calorie of output as food. And second fact is that 75% of the agricultural land what we have on this earth is used to grow soy and corn, which are used to feed animals, and then the animals which are used to feed humans. And then with the calorific conversion so bad, you can imagine that the system is so inefficient. And instead, we could use that agricultural land to directly feed humans. And thirdly, the issue of safety. As you all know, the antibiotics that are produced in the world, most of them or more are used to feed animals rather than human beings. And because of this, the antimicrobial resistance, etc., and the diseases related to it are also rising. So we want to address these three issues via changing the food system to using smart proteins. So really, we have been talking about all of this, right? Over the past decade, we have been talking about how, animal agriculture is not humane, how it is causing antimicrobial resistance, how it is contributing to greenhouse gas emissions, but still there is no real change, right? I mean, if we look at the global meat production and consumption data over the last 40 years, it has been steadily increasing. And the data also reveals that this growth has been the most in the Indian subcontinent and developing countries, and it is projected to grow higher in India and in other developing countries too. So really, our theory of change is we are not going to ask people to stop eating meat, eggs, and dairy because that has not worked and it is not going to work. Rather, why not make meat, egg, and dairy products, using food systems that are sustainable, efficient, and safe? And that is where the category of smart proteins come in. So why don't we create meat, egg, and dairy products using either plant-based proteins or using fermentation-based proteins or using cultivated or lab-grown proteins? So in today's presentation, I'm just going to be focusing on the plant-based protein side of things. But if you guys have any questions about the fermentation side or cultivated meat side, please feel free to reach out to me or anyone in the GFI India team, and we'll be happy to share our resources on those with you. So let's talk about plant-based meat. So this is the definition, and I'm going to breeze through these slides over here because Dr. Gurmeet has covered it extensively. So again, by definition, plant-based meat closely resembles an animal-based meat product in its organoleptic properties. And the three products that you see on the screen, the Impossible Burgers plant-based beef patty, Beyond Burgers, Beyond Sausage, and then there's a Dutch company called Oja, which is making plant-based meat similar to chicken. And you can see how similar they are to the actual animal counterparts of theirs. When we are talking about plant-based meat products, we are not talking about tofu, tempeh, we are not talking about black bean burgers, etc., which have existed for a long time, right? We are talking about products which really mimic meat in texture and in flavor. And this is where technologies like extrusion, like shear cell, etc., come into picture, and that's why they are so important. And we'll be talking about this in the coming slides. So now we are making this plant-based meat from plants, right? So we have plants, and then we get the final product of plant-based meat. But there are a lot of steps that go for this in between this conversion, right? Typically, we can classify this value chain into three segments. The first is crop optimization, wherein, we need to select the right crop, if it is already available, through which you can make your plant-based meat product. Or if it is not available, a lot of companies are actually working to optimize crops, to breed crops in such a way such that they have higher protein, they do not have any off flavors, etc. Second thing, once you select your crop, second thing is you need to isolate the protein from that crop. Uh, because, if you look at meat products, it is, you cannot have carbs, etc. in it. I mean, you cannot have it as much as you have protein. So protein needs to be your dominant ingredient. So you need to isolate your protein and you need to functionalize your protein. So this comes under raw material optimization. And then the third part of end product optimization is where, how do you mix all these ingredients that you have got into, products that resemble meat and texture and flavor. And this is where our end product optimization comes into picture. So let's talk a little bit about each of these three segments of plant-based meat production. So crop analysis and optimization. So as I was mentioning over here, that traditionally crops have been optimized either for yield or either for pest resistance predominantly. But now people have started realizing that, in order to, and maybe these crops are not that functional in plant-based meat products. Yes, we have some, we have ingredient companies working and they have some SKUs of plant protein isolates, but maybe they are not all that functional. So there are a lot of researchers around the globe and a lot of companies actually working, trying to map genomics to, like phenotype exhibited by plants or the functionality exhibited by plants, and trying to see if crops could be bred in a certain way such that they are more applicable to plant-based meat, egg, and dairy products. Now, in terms of crops that are already available out there, which are already being used in plant-based meat products, again, we could classify them into different categories, but legumes and pulses, steal the game over here. A lot of products, what you see out there, use either soy, pea, chickpea, fava, or mung bean, for the reason that they are high in protein. And, if I'm a, protein manufacturer, right, and if I know that, the end product companies want something which is high in protein, I'll start with a crop which has high protein too, right? Because even when I say high protein, it's going to be 30%, but there's going to be still 60% of starches, fibers, etc. and stuff. So I need to work out the cost economics from my end. So that's why legumes and pulses, they are high up over there. But then people have also started using proteins from wheat, rice, quinoa. Seed proteins are coming up big time. An advantage with seed proteins is that you can use the oil and the protein at the same time. So sunflower, pumpkin, hemp, flax seeds are coming up big way. And there are other proteins like potato proteins, which are not used as major proteins, but rather for their functional properties. And here is an example of yellow field peas. So as you can see, it has about 20% protein. And this is a big thing, right? So if we have any entrepreneurs over here who are trying to think if they also want to make proteins that they'll use in their products, you not only need to think about the protein that will go in your plant-based meat product, you also need to figure out what are you going to do with the fat content, or what are you going to do with the starch content or fiber content, because only then will your cost economics really work out. One of the reasons why soy is so cheap, like soy protein isolate, when compared to others, is because soy has been optimized for decades, and each and every fraction of soy is used for something or the other. And that's how you can get the protein cost down. But if you don't have any use for like the starch component or the fiber component, then you compensate for it by increasing the cost of the protein, which will lead to less consumers for your products. So just something to think about. Here is kind of graph showing that percentage of plant-based protein products in the market. Soy is still leading for various reasons, but peas catching up, as Dr. Gurmeet was mentioning. Wheat is also, people are using wheat for the positive organoleptic effects that it has on the product, etc. Another thing which I was adhering to earlier is that even though we say that soy has been optimized a lot, and soy protein isolates are isolates that are used by food companies, one thing that we need to understand is that soy was primarily optimized not for protein but rather for its oil. People wanted to extract oil from soybean, and then they started figuring out what to do with proteins, and that's how they started selling it in the market. But then this was a thing of the past, right? Now after the entire wave of plant-based meats has started, people are actually, changing the extraction processes a bit too, or trying to work around it to see that how could we even extract, or refine soy in such a way such that, we can get the oil, but at the same time, we can also get a functional protein or even more functional protein. Similarly, wheat was optimized not for its protein, but rather for wheat starch, which is used in bread throughout the globe. And pea, similar thing for pea starch. So this is again something, just keep on back of your head. And I say this because, you may work with soy protein isolates and you may say that this isolate is not functional. But then companies also realize this, right? Companies which are really focusing on, creating plant protein ingredients, they realize this. And, just a simple change in the extraction process of oil, or in the defatting step can make your protein isolate more functional. So something to think about. And I'll be talking about steps of protein extraction in my coming slides. And this is what the example was, what I was saying of wheat and its conversion to bread. So really with crop optimization, it's about how do you, like few of the areas, if you're thinking about, setting up a company in the crop optimization part, or want to think more about it just in general from a research standpoint. So for the crops that are already available, how could you breed them in a certain way such that you increase the nutrition, you can increase the functionality and performance, while at the same time keeping the cost same or driving down cost. Uh, there are companies around the globe which are doing, this work. Equinom is a company in Israel. You can check out their websites, which is strategically breeding different seed varieties, and trying to get better functional properties out of them. There is Benson Hill company, which is actually, breeding soybeans, which have 60% protein instead of, around 20 to 30%. Because what they are saying is that companies spend huge amount of money in just trying to isolate soy protein from, soybeans. But if we make soybeans with about 60 to 70% protein, then you can skip this whole stage, right? You can really save a lot of money over there. So this is an interesting concept. So you can check out their website too. The second one is raw material sourcing and optimization. So what happens over here is once you have decided that, okay, this is the crop that I'm going to use, you need to extract protein from it. And there are various ways of going about it. And secondly, sometimes these proteins, what you get are not functional. So you also need to functionalize it using various physical methods, chemical methods, etc. So a lot of good work is happening over it too. A lot of big MNCs like ADMs and DuPonts and Rockets are working on this, and so are a lot of innovative startups. Here is a graph, a typical way of extracting protein. You start off with your raw materials, you dehull them, remove your, the inedible hull. Then you mill them into flour, and then you extract the oil out. And as Dr. Gurmeet was mentioning, this becomes slightly critical, or this becomes critical in extrusion process, because when you have fats, your product tends to slip and may not get the shear that it should in an extruder. And then post that, once you have the defatted flour, there are different steps you could use, like isoelectric precipitation, filtration, etc., to really get extract the proteins out and also separate it from starches, fibers, sugars, etc. I'm not going to go dive deeper into this further. We actually have this as a white paper resource in our resources section on our website, so please feel free to check it out. So the things that we need to consider as we are selecting, our plant proteins for our extrusion process or plant-based meat creation process, right? One is definitely protein content, the protein quality, as Dr. Gurmeet was mentioning, the functional properties. But at the same time, there are a lot of other things that you need to consider, right? Like one is, if you are trying to use a very novel, XYZ crop, and you figure out that it is really functional, you also need to know whether it is approved from a regulatory standpoint, right? Otherwise it will take you a couple of years just to get it approved, from a regulatory standpoint. So that is one thing. Second thing you need to understand is just the how much of it is available, right? Okay, fine, you found this crop, it is really functional, but people just don't grow it anywhere in the world. So how do you really work around it? Cost is another big thing. You always need to do your cost economics when you're deciding for any ingredients. Allergenicity, if it's a new crop, you need to pass it through an allergen testing protocol, etc. So a lot of things to consider. And just to give you a few examples over here. So if you look at soy, its PDCAS value is really high, right? So good source of protein. So protein nutrition is green in color. Green means good, red means not good. But it is also considered an allergen, so that is not great. Flavor, soy still has some off flavor, which is not great. But then in terms of functionality is really good, crop supply is really good, cost is also pretty decent, and a lot of companies have started using it in their products too. Comparing it with P, right? The nutrition may not be as great. So the PDCAS value of P is just 0.64 compared to soy, which is greater than 0.8. But then it is not as bad of an allergen as soy, right? And the flavor is also slightly better or slightly neutral, we could say. But then the issue becomes crop supply. There is not as much crop supply available for P as there is for soy. But still, companies are working around it. There are products which have launched, using P, etc. So these are the things to consider. And again, I'm not going to walk through this, the table over here, but this kind of, you could take a note of this as some things, as product developers, as you're building your ingredient portfolio to create your extruded products, some things to think about, so that you shouldn't come at such stage where you spend a lot of money and a lot of time and a lot of energy in, getting your product development ready and, all your pilot trials done, but at the end you realize that, oh, this is not approved at all, or oh my god, I did not think that this was an allergen risk, or oh, I'm never going to be able to get the crop volume that I need to break even, etc. So it's not just about proteins. There are other ingredients too that go in plant-based meat products, which are as important. There are different binders. Dr. Gurmeet also mentioned. Now, this could be, you could add these during extrusion or post-extrusion, etc. Which really, if your protein is lacking in some functionality, or if your product doesn't have, for example, say freeze thaw stability, then you could add certain binders to, give the freeze thaw stability to a product. Colorants are very important because they come under sensory acceptance, right? Like, people are used to a certain color of chicken or a certain color of fish, and if they say that the color is off, they may not buy your product again, etc. Oils or fats are also very important, because consumers are used to the fattiness or the creaminess what these animal products usually tend to give, and you need to have a proper mixture of fats to kind of stimulate that sensory experience too. So now that you have worked on all your ingredients and you have it ready, the third part is end product composition and process optimization, right? And this is where you actually get your structure together using extrusion process or other process. You optimize your process further. You do a sensory evaluation. You do your compositional analysis. You check what flavors are present in your product versus what flavors are present in, say, a chicken breast, etc. And then you keep doing the stepwise product development. Various texturization processes to do this. And I think I have a few slides now, which Dr. Gurmeet has already covered extensively. So I'm again going to breeze through them. Extrusion cooking is the most commercial, or probably the only commercial process right now. But there are also other processes like shear cell technology, 3D printing, electrospinning, which are under various stages of development. So here is an extruder. Again, two types. There are low moisture extrudates, high moisture extrudates. And again, two types of products. If you're making your chicken keema product, then probably you would use low moisture extrudates. And your product development process would be different, versus if you're creating your whole muscle products, it would be different. These are the steps. And again, we have published a white paper resource on this. You can find it on our website, or you can reach out to me post this presentation, of just the entire process flow to create a restructured plant-based meat product. Similarly, an entire process flow to create a whole muscle plant-based meat product. And yeah, if you have any questions, reach out to me later. There is also shear cell technology, which is currently being developed at Wageningen University in the Netherlands. The advantage of this technology is that you could actually create blocks of meat. You're not restricted by a die size. And there is a company called Rival Foods, again based in Netherlands, which is using this technology to create plant-based meats. 3D printing is also coming up big way. There is a company a company in Spain called Nova Meat, which has demonstrated success. Again, they aren't commercial yet, but again, they are carrying out their pilot trials. Similarly, there are companies in Israel called Savor Eat and Redefine Meat, which have again, printed 3D printed steaks, 3D printed bacon, etc. So something interesting, to think about and to look at. And this is about product optimization, right? And Dr. Gurmeet already mentioned this, using texture profile analysis. And I think the figure to the bottom right of the screen is actually taken from an article published by Beyond Meat. So this is the exact same thing that Dr. Gurmeet was mentioning, texture profile analysis to really understand the hardness, chewiness, resilience, and then comparing it with the animal counterpart. At the center, you see a gas chromatogram, wherein, I think they have looked at beef, the flavor compounds present in beef, and then trying to see how we could replicate these flavor compounds in our plant-based beef product. So here's the Impossible Burger. Again, we usually show these slides to kind of let participants understand that you see a lot of ingredients on the screen over here, right? 21, but really if you split it up, they have particular function, and that is why they are there. So we have proteins, then which form the bulk of the product, and then we have some binders, we have some colorants that they have used, vitamins and minerals that the product has been fortified with, preservatives, flavorings, and at the bottom you can see the process, like how they make the impossible patty. But I think what I would like to cover over here, which is a positive thing, right, with plant-based meat, and given that people in general are becoming more health conscious and nutrition conscious around the globe, and this is taken from Impossible's website, right? They are comparing their Impossible product to a 80/20 beef burger, and as you can see that this product has got same protein level as the beef burger, but at the same time it has fewer calories, it has less saturated fat, it has no cholesterol, it has higher vitamin and mineral and fiber content. So this is a great thing, right? And this is the advantage of creating these products using plant-based proteins or a fermentation platform or a lab-grown platform, right? Where we could really get the things that we want, but at the same time we could eliminate the things that are not so great about these products in terms of nutrition. Okay, so in terms of companies working in the space, again, a lot of companies, Impossible, Beyond, Corn, these are like sort of path leaders. But then again, there are also other companies, like big companies like Nestle getting into it through their Garden Gourmet brand, etc. And when we are talking about plant-based meat, we shouldn't just think about the final product companies, right? We should also think about the ingredient companies like DuPont's, which are supplying the plant protein isolates and modified starches, etc. About AAK, which is supplying like specialty fats and oils to replicate that fattiness in the product. These ingredient companies which are making it possible, and at the same time, like technology companies. We had Brabender present, like Brabender has made these extruders, because of which creating these products are possible. Similarly, Klextral, Wenger, Rival Foods, etc. These are all creating technology. So I wanted to bring this slide up because if we have student participants in this workshop today, if you're just thinking about entering into this space, right, there are various avenues you can enter. If you're more engineering focused, you can see if you can join any of the like Brabenders or the Klextrals, etc. But if more chemistry focused, etc., you could look at DuPonts and AAKs, etc. Now talking about the market for these products, as we all know, that meat alternatives are going mainstream, right? Burger King, every Burger King in the US, and first I'll be showing some Western data from the Western countries, and then I'll be talking about India. So every Burger King in the country has meatless Whoppers now, and as you all know, in 2019, Beyond Meat had one of the most successful IPOs ever. Pretty much all the QSR chains in the West are carrying these products now, right? Right from McDonald's to Hard Rock Cafes to Subway to Tim Hortons, etc. Companies, and this is no longer restricted to like startups, right? Like big companies are entering, but what is even better is that traditional meat companies like Maple Leaf, which is one of Canada's biggest meat companies, are also entering the space with their own brands or by investments into like startups, etc. Because they realize that this is a sustainable way of food production, and this is where the world is going to go to. So again, this kind of graph just shows you the market and how it is increasing. So if you look at 2017, about 1,000, not even 1,000 QSR, channels had, plant-based meat products, but come to 2020, more than 30,000 food service channels have these products. Similarly, in retail also, again, if you look at 2017, maybe there were 5 to 10 products in retail for plant-based meat, but 2020, there are more than 30. So this is growing across the world for all the right reasons, and it is a good time to be in this space. Uh, if you look at the market projections, again, there are a lot of companies are working on just estimating the market, etc. So the global plant-based meat market is projected to reach at least $100 billion, if not 370 billion by 2035. And please do reach out to us. We have more extensive articles on this. We publish what are known as state of the industry reports, and we have published them for 2018, 2019, wherein we have kind of put down the investment landscape in detail. So we could share those with you too. Now, when it comes to India, plant-based meats are gaining acceptance in India too. And so this was a study conducted by Ipsos, and wherein they asked, consumers from different countries if you would consume a plant-based meat substitute. India actually scored second in this. So in China, people said that they would, 73% of the people said they would consume plant-based meat substitute. And in India, it was second, where 63% of the people said they would consume plant-based meat substitute. So there is definitely market in India. It's the same thing. But when it comes to India, I think more than beef or pork, just because people just consume more of poultry and mutton, the market for getting plant-based meat products based on poultry or mutton would be higher. So that is something to note as you are going along your product development cycle. Another interesting point about India is that even these products, what you see on the scale, which have been shown earlier or in the market, right? These are burgers, right? It's the Impossible Burger, it's the Beyond Burger. Yes, they have other SKUs also, but the burgers are what it is popular for, because Americans consume a lot of burgers, right? Like 3 burgers a week, and have just one hero category. But in India, we have multiple national dishes, right? National dish could be, people from the south could say their favorite dish is something different versus from the west versus from the north, etc. So this also leads to a lot of market for different players, like different regional players, and also a lot of room for innovation, right? Like, a company could actually focus on kebab like products, whereas one company could focus on high moisture meat analogs, just for biryani. And I think this was highlighted earlier too, right? That in India, another peculiar thing is our cooking methods, right? We have just so varied cooking methods, and whatever product we make, it needs to withstand all these different cooking methods with different spices, etc. So a big innovation opportunity. QSR chains in India have started realizing that they need to, just offer these products because people are asking from it. Bheros has like a Kathal biryani. Subway has launched its Keema subs. And another thing is Domino's. You might have learned like few weeks back they have launched what is known as the unthinkable pizza with plant-based chicken. So I think. Okay, so this is where we are in terms of market. So there is a big, big need in the market, and lot of innovation to be done. So it is a good place to be in and a good time to be in India. Now, my last section of the presentation today is, at GFI India, we are trying to work with all the stakeholders in this ecosystem. So we are very grateful to Dr. Gurmeet, Abdul, and the team at TDU for hosting this webinar today, because, this workshop today, because this is what we need for this ecosystem, more awareness, more technical expertise like Dr. Gurmeet and Abdul's, so that more products can be made. And at GFI India also, we have various initiatives through which we try to engage with different stakeholders to build this ecosystem. So I'll walk you through the different initiatives, what we have. Last year, we conducted from August to December what we call the India Smart Protein Innovation Challenge, wherein we had more than 1,000 participants from 100 plus universities in India, and they all participated in creating plant-based meat, plant-based eggs, plant-based dairy, plant protein isolates, etc. And it was a pretty intensive process, right? Because they got certified via world's first smart protein digital lab certification, which we created. And then, we gave them the participants, we organized workshops for them with different investors and, people from different professionals who could contribute to them developing the product, launching companies, etc. And that resulted, at the end of the journey, it resulted in like 10 companies who were selected in the final round, and they had the opportunity to present their ideas to investors, and other technical experts, etc. And a couple of them have also started their own companies now based on this challenge, and will be launching another version of the challenge this year too. So please stay tuned for it. We also organize summits. So in 2019, we organized what is known as Future of Protein Summit. And in 2020, we organized a virtual Smart Protein Summit, which was again a great event because we had 2,300 plus registrations spread over 5 days. We had keynote sessions with Indra Nui, with Josh Tetrick, and then addresses by a lot of eminent personalities from industry and academia. So we have videos of the Smart Protein Summit on our YouTube channel, GFI India. So feel free to check them out just for you guys to get a better idea of where the industry is at, what are the developments happening, what collaborations can happen, etc. In addition to this, we also have a 12 lecture course ready to go. We have already launched this course at 2 universities in Israel, and we are launching it with 2 universities in US and one in Singapore this year. And we also want to launch this course at universities in India. So if we have any academic stakeholders over here, feel free to reach out to me and we could discuss more. We also have GFI's research grant program. In 2019 and 2020, we awarded $6.6 million to different research groups around the globe who were focused on improving the organoleptic qualities, cost, and scale up of alternative proteins. So again, if you're an academic stakeholder, if you're from a company and you would like to know more about how you could get and this is a competitive research grant program, but how you could apply to it, to reach out to me. This year's RFP has just launched on 26 January. And again, projects are funded to the tune of $250,000. And the first deadline is on 10th of March. So there is still time to put your proposals together, look for collaborators, etc. We have also launched what is known as the Smart Protein Ecosystem Database. So this is like a one-stop shop, right? So a lot of times, as a product developer myself, I've faced issues where I want to, purchase some ingredient, but then I just don't know where to look at, right? There are different websites, industry forums, etc. So we have developed this wherein we have listed, ingredient suppliers, R&D consultancies, equipment manufacturers, university professors who are open to collaborations, etc. in one database specific to plant-based meat, egg, dairy products. So please reach out to me. I can share access of this database with you. If you're a stakeholder and want to be enlisted on this database, please do reach out to me and I can send you an intake form for it too. We have other plethora of resources. We have also launched a podcast called Feeding 10 Billion, wherein we have interacted with eminent academicians, eminent industry people, where they are talking about their journey of how they have started their plant-based alternative protein company, etc. And we also have a lot of other technical resources. I was sharing the graphs from these resources in my slides earlier. We'll also soon be launching what we call the India Good Food Startup Manual. So for all our entrepreneurs out there who are looking to start companies in this space, this would be like, again, a one document, right? Where you could read about how to start your company, what is the stage gate process, what do you need to think about when you are incorporating a company, etc. So all the details would be over here. We also do what is known as strategic analysis. So people who are looking at exploring like novel proteins for that matter, or novel technology areas, we do a thorough sort of technical analysis and kind of figure out what are the opportunities that exist in this particular area. So we did something similar for algae, right? We evaluated microalgae and seaweed right from strain selection all the way through creating meat analogs from this algae. And then we identified, so in cultivation, there are actually 3 opportunity areas or 3 areas where companies can be formed to really ease the value chain. Or in protein extraction, there are still these 2 or things that need to be worked on. Our opportunities dashboard is already out, so you can check this out on our website, and we'll be launching a technical paper on this soon. So that's all I had. So again, I would like to thank everyone over here. And if you have any questions for me, please do let me know. Or you could reach out to me via the email ID what I've listed on the screen.
Thanks, Siddharth. That was a wonderful presentation, and I think a lot of ideas in there. Even I can see a number of taken down a new number of actions to connect with you on. Right from that university course that you were saying to that startup challenge that some of my students could be interested in. And I think the database certainly would be helpful. And I'm sure for the participants as well, this is a great resource, I think, on protein. So if there are entrepreneurs here on the call, and I think that's a GFI having an India leg to it is a great resource to reach out in the same time zone in some manner and connect with people. So I mean,
Definitely,
just
Dr.
one thought. One personal experience. I think you mentioned about how things are changing, where protein used to be a waste byproduct almost. If I look at 3 decades ago, to becoming one of the primary byproducts, agri products or dairy product. I mean, my experience was with the dairy industry, and I was doing an environmental engineering course, designing wastewater treatment plants. Where in the dairy industry, the problem was, what do you do with the whey, right? Whey, whey was a waste that you had to handle in a wastewater treatment plant. And today, whey protein is like skyrocketing in terms of demand. No, there is not enough whey that we get in the dairy industry. So how things change, and that's what success is when we are looking at when we look at protein as the primary source in a lot of these newer protein sources, agri sources. What do you do with the rest of the stuff, the starch stuff, the fat stuff, the other value added stuff? And if you can create that holistic picture, a supply chain for every single fraction of a agri product, then it's easier to succeed. Yeah. Right. Yeah.
Totally agree, Dr. Gurmeet. And that is what we learned even with our algae strategic analysis, right? When we were talking to different players who are actually making algae and basically making carrageenan from it. But when we are talking to them about, making proteins, one of the things was that, we really need to employ like a biorefinery approach, wherein we use all the good positive health benefits from algae, but protein and carbs, etc., to make it economically feasible. So I think that exists across all sort of crop chains.
Correct. Any questions from the audience?
I see a question.
Couple of questions there.
Yeah. Wondering jackfruit as a plant-based meat. So with jackfruit, the thing is, there are a lot of companies working in the area of jackfruits, right? They are trying to evaluate different varieties of jackfruit, different ways of processing a jackfruit to get it similar. So a lot of work is on jackfruit. But then again, like I feel that the kind of texturization or fibration that you could create using processes like extrusion or shear cell, uh, I think that they would just give you a product closer to meat than using just jackfruit, uh, unless there is a certain variety which has certain textural properties which is just unexplored, or certain processing methods that are unexplored. That would be my opinion. But again, Dr. Gurmeet, would love to know your thoughts also on it.
Yeah, I mean, we have personally not played with jackfruit yet. I mean, we have it on one of our list of things to do. But I also agree with you. When I look at jackfruit, I'm not looking at it as the main source for fibration. I think fibration, we will get better fibration with these 4 or 5 different lead proteins that we have, and that's where all the fibration excitement will stay. Jackfruit could be an interesting component to include because of its it certainly brings in a certain flavor, which is a meaty flavor that it brings in. So I look at it more from a flavor perspective as opposed to a texture perspective. I think texture you can outdo with some of the other ingredients today, right? And it'll take a long while for jackfruit to match up to that.
Yeah. I think there's another question. What would be your advice to someone looking to begin a vegan meat manufacturing company? So I would say that if you could connect with us, do reach out to us. So we have like an innovation department. So my colleagues, Mr. Shartul Dabir and Nicole Roque, they are actually experts in this, where they could guide you through the various activities, which you could take part in to help you launch in your vegan meat company, and also share resources with you. There is another question. Do you see a way in which electrospinning can be used in combination with extrusion technology? So there is a company called, I believe, Cyber Colloids, which is based in the United Kingdom, which is using spinning to actually create these fibers, which they are then aligning to create plant-based meat. So it is possible. People are again showing, but I think it's about executing something, but also scaling it up, right? So I think they are different people are in various stages of product development and scale up, but it's definitely possible. a prototype has been shown, which has been successful. So yeah, so there is again, and it's again unexplored technology. So if you have any ideas, there are a lot of research papers out there on spinning technology too, and how it has been used to create, like fiber-like textures. So that's interesting. There's another question. How do you see consumer acceptance in this category, considering that a lot of Indians still think that their daily diet need is being taken care by pulses, non-veg options, etc. Uh, this is how we'll answer this. I'll answer this question, right? So this is a question which we get a lot, and especially we get this a lot to the GFI India team, like because we have a lot of people who are vegetarian, right? So who are like, oh, you're working on all this plant-based meat, etc., etc. But I don't even consume meat, and if you're trying to make the meat product similar in texture and flavor to an actual meat product, then I won't even like it. So that's why we always say that there are two types of products over here, right? Like one thing is also high protein products. I would say that one thing with legumes is that even though you are consuming say 100 grams of, like if I consume 100 grams of tur dal, right, I'm still consuming about 70 grams of carbohydrates with it, right? Which maybe, if I'm a fitness enthusiast, etc., maybe I do not want that. I want more isolated form of protein. So I think there are companies in India who are working on creating not products similar to meat, but just rather high protein functional products, right? So that they could add in their meals, etc. So that protein needs would be answered that way. Yeah, and then for the non-vegetarian population, it's the plant-based meat product, right? The plant-based meat products that we are preparing are for the flexitarians. Really, they're not really for the vegetarian population, because they're not going to like the texture and flavor if they don't consume or they don't like meat products too. So there are two classes of products over here. I think there's another question, which is India's impossible or beyond? What kind of sales turnover have the exciting companies achieved? So again, I don't have this data. I know that Good Dot is probably the biggest plant-based meat 2.0 company in India. Yeah. So and they are doing pretty good, right? They have a lot of they have this QSR chain called Good Do. They just launched last week another SKU, and they have like 10 SKUs already over there. So they are innovating. The market is also gaining more traction, so it's just bound to grow. Okay, so the question is, aren't there already established plant-based meat companies that are way ahead in the cycle, and won't the market just consolidate with a few top companies? Are there still opportunities? I think there are still opportunities, right? Or maybe like Dr. Gurmeet, with his extensive work experience over here, would be able to answer this question better. But I think there is market for innovative startups to come up. And from what I have heard interacting with large conglomerates is that they are still they already have a lot of products, right? Whereas with innovative startups, they focus on one or two products, and it's faster for them to launch these products, to get the consumer research and get them out. And then post that, like how we have seen in the West, right? It was Beyond and Impossible who first launched products in the space, and then Nestle came in later after a few years with their Garden Gourmet brand, and now PepsiCo has come and said that, oh, let's do a JV with Beyond Meat for some products, etc. So that's the trend we have seen in the West. But with respect to India, I would like Dr. Gurmeet, sort of give his thoughts on this.
Yeah, I mean, I think we're just starting out on this journey globally. I mean, even though they may seem like there are a few companies which are the leaders, I think we're just starting out on this journey. And I think, again, to the point when you answered the last question as to what are the types of consumers, we haven't even completely identified the various consumers, the target groups, and what would be the triggers. I mean, that requires a lot of consumer understanding. We're just beginning with, there is an interest in protein, there is flexitarianism on one hand, and then there is the protein source that can be have enriched protein and lower carbohydrates, so meal balancing in some way is one, but there will be so many other categories that we could identify through consumer work. But in terms of products, again, I mean, to one of your slides towards the end, when you pointed out, if you look at India, there is no one big product in India. No, just like burger defines 3 times every week. Here there are so many different products, and each one of them requires its own innovation. So for startups, you could pretty much decide, if you focus on, my suggestion will be focus on what you're trying to do and focus on what is your target consumer proposition with it. I mean, so for example, you mentioned biryani, right? Biryani ke liye, what is the best possible meat? I mean, just look at, for example, this product which is becoming very popular suddenly, right? I mean, 3 years ago, nobody had tasted soy chop, right? Which is available in pretty much every veggie chain right now. And it has become popular. It's mostly vegetarians who are eating it. So, and it is a very simple product today, made from soy nuggets and soy paste rather than texturized. It's not a texturized product. So that's ground zero. And even that is showing traction. So if you start building on it, the whole texture flavor game on it, there are a number of such products, and they will go into the Adyar Bhavans and the Udupi dosa joints as well. So it is not just going to be Subways which are leading this, and Domino's that lead this revolution. It's for us. It's going to be limited based on our imagination. I think you could imagine. I can imagine a dosa getting stuffed with a filling, no, a vegetarian filling. As a very balanced meal. I mean, it's even now super protein, right? It's not just the dal in the dosa batter, but it is also the filling instead of potato is now a protein filling. So somebody needs to. So these are all different innovation ideas that one company will pick up, right, and become an expert in. The consolidation will happen, but that's way later. And I mean, consolidation happens. You look at tea. There are 3 or 4 very big brands globally. I mean, but so many other tea companies, right, in the world, which are making very successful small companies. So there is always. So I think we shouldn't worry too much about consolidation at this stage. Yeah.
Okay. I'm just checking if there are more questions.
Somebody was asking how to reach out to you. Kagun was asking, but I think if
yeah, I could just
yeah, you flash your contact email once again, maybe.
Yeah.
Otherwise, if any of you want to reach us, you reach out to Abdul and he will pass on Siddharth's email to you.
Sounds good. Dr. Gurmeet, do we have time for like one more question or?
Yeah. Go ahead.
Okay, so there's one more I see. Everyone assumes that plant-based foods are healthy in general. What's your guidance for startup who is trying to navigate vegan food from healthy eating? Can the processed food be healthy as natural one? Uh, okay, so this this is a good question, right? But okay, so I feel like coming from a food science standpoint, right? Me cooking rice is also processing, right? In one way, like the rice what we eat at home, like if you look at the rice in the field, it undergoes like a lot of processing, right? Like dehulling, like debranding, etc., and then we cook it, etc. So really then comes to what do you define as processing and what is not processing, right? And I think Smita, one of our entrepreneurs, like I think she had asked a question too, that she's trying to create plant protein isolates using green technology. So this processing is it's not going to it's actually going to improve like the nutritional qualities, right? You're going to get like a 70, 80, 90% pure protein without any like chemicals or anything else added to it. So and as Impossible has showed right from its the slide what I showed you, right? It has same number of protein, but it has less saturated fat. It has less other things like more vitamins, more fiber, etc. So in fact it is better, right, than the traditional 80-20 burger. So I would say that as long as one is mindful while creating products about using ingredients which are say label friendly, which have been processed using green technologies, and then you could always do your nutritional analysis on your final products. You could, and even Indian regulations, right? For me to use certain ingredients in my product, it needs to be approved by the FSSAI, right? And FSSAI does extensive research before approving a certain ingredient. Even if it does, it approves only up to a certain quantity in a certain product, etc. So that makes me believe that these products are as healthy, like as any animal-based counterparts. And with plant-based meat, we also have the option of modulating, as I said earlier. Increase the positive things, decrease the negative things. Okay, so there's another question I see. Meat has become cheaper like veg in India, and meat market has grown. How do we see cost impacting India consumption? Uh, I would, Dr. Gurmeet, would you like to add your thoughts here, like based on your experience in terms of cost and consumption of products?
Yeah, I mean, meat today may seem cheaper. I mean, poultry may seem cheaper in India. I mean, because pulses are expensive and poultry, because a lot of investment has gone over the last 2 decades has gone into poultry farming versus pulse farming in some sense. No, and it's the skew of policies, I would say, which have also led to that imbalance in real cost. But if you start putting in real costs, no, which is going forward from here, and you look at the energy required for, I mean, energy is going to be the driver, right? The environment sustainability is going to be the driver from here onwards. Then clearly veg proteins are going to, I mean, all the indications are towards veg proteins from here onwards, which is why you see, and the data that Siddharth also presented, all the big companies, it's not just the brand companies, but even the meat companies are beginning to say that, hey, veg proteins is my core. They are reimagining themselves as protein companies as opposed to as meat companies. That's the big shift which is happening. So going forward, the traction is going to be towards veg proteins. There's every indication to that. Yeah. And I mean, and this is not that animal proteins will go away, right? But it is where is the next 2 billion population going to get fed? Yes, partly from animal proteins, but mostly from veg proteins. Otherwise, we do not have a planet, is how I feel. I mean, uh, if the energy that we're talking about today, which is required to get animal proteins, we don't have a planet when we are 10 billion. So there is no option in some sense. Another similar question that for you, is there ask for green tech?
There is an ask for green tech to do something the food system to be healthier one. What would it be? Sorry, I don't understand the question. Could you? I mean, if Vijay, if you could come off mute and you could ask it too.
Hello.
Hello.
Yeah, you hear me?
Yeah, Vijay, we can hear you.
Yeah, what meaning green is
Vijay, we can't hear you.
Hello.
Vijay, you're very soft. Your voice is coming very. If you can be closer to the mic or speak louder.
Can you hear me now?
Yeah, go ahead. We'll try and
No.
understand it.
When we like taking the deep analog of the plant proteins, we see the green phase. See, we are going to plant food, right? How that will affect like climate change? How?
Vijay, sorry, we can't hear you well enough. Yeah.
Yeah, Vijay, we can't hear you. Maybe we could just email us and we could get back over email.
Yeah. But Vijay, I mean, green tech, you could think of plant meats as one part of green tech, right? Yes, there is, I mean, green chemistry is involved. So there would be many opportunities for entrepreneurs to look at protein extraction, etc. and make that greener as well. So, I mean, even in the veg protein setup, there are many asks of green techs, green chemistry, green physics, green processing, green fuels, which will be required, besides green tech for all other food systems. But plant proteins will play a major role there as well. I mean, another pointer to, there was a question, just to the previous question, where are the innovation opportunities? Our slides show right now, when we talk largely about soy proteins, pea proteins, and wheat proteins as the big ones, right? I mean, the chart also showed those are the three big peaks, right? We have in my kitchen, I have 10 different types of lentils and pulses and protein sources that we use. Many of them, it's waiting for entrepreneurs to look at and make them into what kind of textures that they give, right? And for me, one of the excitement is that it creates a new texture. I mean, food for the today's generation, urban generation, at least, food is about, there's a lot of foodie, right? That what foodie is about, creating new flavors, new textures, new experiences with food. And while I'm used to eating rajma in my rajma chawal way, but I am very open to creating a new product out of a new texture, a new experience of out of that rajma as well. So if somebody could give me a rajma granule or rajma bean which is restructured with maybe chewiness, I don't know, it could be an opportunity, right? Who knows? Yeah. So that's the new product innovation phase, that how are people reimagining things. You know, think of rice, for example. Today, one of the big innovations in rice is fortified rice, right? Which is, and it's a must now, mandated by FSSAI, by the Government of India, by the Food Safety Standard Authority of India, where they are saying, because half of Indian population is or pregnant women or women at the pregnancy are anemic, and maybe 30% of normal population is anemic. We are dictating as a country that all rice needs to be fortified with iron, just like salt is fortified with iodine. And for that, the technology is almost like an extruder technology, right? It is that you take rice, you grind it down into a powder, you put it through an extruder along with an appropriate iron source, so that iron gets absorbed into the matrix of the rice, not on the coating, not on the surface, because then it gets washed off. And then you extrude it out and convert it into a rice shaped, restructure it as a rice granule. And this rice then gets blended in normal rice at 5% or whatever, and we have fortified rice. So that's fortification of rice with iron. And what we are talking about is protein, which is another hugely, another nutrient in which a large part of the population is deficient in. So number of opportunities here. Okay, any other question, or I think if we are done, if any other questions, please send through emails. You have all our emails. You have Maria's email, you have Siddharth's email, you have Abdul's, and you have mine. So please get in touch. And thank you so much to everybody who participated in. It was wonderful to touch the audience 50. I mean, the mark of 50. That was amazing. I hadn't realized that there is so much of interest in the meat analogs sector, the smart protein sector. So it was quite exciting for us as researchers to see this kind of an interest, and quite an engaging session. There were a lot of good questions. I'm sorry if you couldn't answer everybody's questions, but stay connected. And thanks to all the speakers as well. Maria for joining all the way from Germany, for Siddharth from GFI, wonderful presentation. And to Abdul, who spent a lot of his time putting all this together and creating all the videos and doing the lab work and putting it all together. Thanks to Abdul and to Shubham and Manoj, part of the team of doing all the experiments and getting the things together, the data together. So thank you, everyone. You want to come on a minute, Abdul, and say a few words? Abdul, Manoj, and Shubham.
Thank you, sir. I think this was a very great workshop we did today, and hoping to do these kind of workshops in the future. And another thing I would like to tell that so in the next month we are conducting an online hands-on workshop in the TDU campus, which is on 24th, 25, and 26th February. And I'll be circulating the advertisement, the brochure, and the invitation link. People who would like to register, they can register us. And thank you, Dr. Gurmeet sir, and thank you, Siddharth ji. Thank you, Maria, and thank you, Jay Kumar ji, for joining and present for the presentation. And thank you all the participants who have participated, and thank you everyone.
Yeah. Cool. Shubham, Manoj, you want to come on and show your face and say hi to the audience or a bye to the audience? Because Shubham and Manoj are always behind the scenes, yeah, most of the time, but very critical to the workshop.
Hi,
hi Manoj.
Hello, everyone. Yeah, and I'm very thankful to all to participate our event, and this is a very good interaction with all of you. I hope all have enjoyed this session.
Thanks, Manoj.
Thank you, Manoj.
Thank you. And Shubham, are you there?
I think, sir, he is in another call.
Oh, he's another call. Okay.
Yeah.
So thank you, everyone. We'll end the call today and stay in touch. Okay. Bye-bye.
Thank you, everyone. Bye.
Bye. Thanks, Siddharth. Bye.
Thank you. Thank you, Dr. Gurmeet.
Bye.
Bye.